So let's jump right into it. Here's the solid model of our part that would have been delivered by the customer. No dimensions, we don't really care. We're going to look at a paper print copy of this here in just a second. But before I get into any kind of programming, obviously I want to study this part and figure out exactly what it is that I want to do. So it looks fairly straightforward. There'll be some OD turning, a couple of grooves. We've got a thread, a drilled hole in the center that's flat bottom, nice little chamfer here. It looks like we got a radius on the outside, a little counter bore, a couple of fillets. Let's take a look at the actual print. There we go. So we've got a 2-inch 12 TPI thread. It's 2.5-inch final OD, so that tells me right off the bat, hey, I'm going to need to start with stock that's greater than that. You could use 2.5-inch diameter stock, but then this feature here will not necessarily be concentric, nor will it be cleaned up unless we get really lucky and our material comes in a bit oversized. So let's just plan on using 2 3/4 material. And there I've got some call outs for those edge breaks I noted. A couple of call outs for the width. They're not calling out an edge break here on the groove, but I'm still going to do it just because I like to be nice and clean. And now let's look at the ID print. Looks like we got 1.25 inch depth on this, 750 diameter. Now it doesn't say so on this print, but I'm going to assume, just for the sake of this class, that this is not a tight tolerance. I'm just going to pop that with a 3/4 inch flat bottom insert drill and be happy with it. They do call out an edge break here, so I will be tied to 50 thousandths by 45 degrees, and then we've got a counter bore on the outside. So now that I'm familiar with the part, I want to stop and think about the tools that I want to incorporate in using this. So now I need a process idea and start incorporating my tools from there. So here I have a blank piece of paper with my process list. I like to write this down so that I can keep track of features and just keep everything straight in my head. This is pretty formal, having this nice little process list form. It's not a bad thing to have, but certainly a piece of scratch paper and a pencil will work just as well. Before I start making this process list, I want to put a little asterisk on this, and I'm sure that some of you out there are going to say, no, this is how I would do it, or I would do it this way, or I would do it this way. Nothing is ever incorrect if you get a good result. So you feel free to object and or do your process in a different order. If you get a good part off the machine at the end of the day, you did it right. I'm just going to use what I know and what I've learned in my experience as being, the right way for Charlie. There's always going to be a right way for you guys, and hey, knock yourself out. Again, if you get a good part at the end of the day, you won, you're done. So the first thing I want to do is I'm going to start easy. I'm going to face this part and rough out the OD. So on my process list, I'm just going to tell it that the first thing I want to do is a face and turn, a face and turn. Process number 2, I would imagine that now would be a very good time to pop that ID, pop this little hole here. And the reason that I want to do this now instead of doing all of the OD features and then all of the ID features, this is a fairly big size. I'm planning on using a flat bottom inserted drill that's already 750 or maybe slightly smaller so that I can skim cut that with a boring bar. But that's still a large size, and that's a lot of tool pressure that could possibly deform the material. So if I had a tight tolerance on one of these features, if I laid that in complete before I popped this hole, then it could move that dimension ever so slightly and put me out of print. So my strategy is, let's rough the OD first, And then the second thing we're going to do is the second most aggressive, which is drill that centerpiece out. Once I've got that drill out of the way, now I can go in and let's just pick a feature. I think I'm going to do the groove. I can do this groove complete with my groove tool, and also I'm looking at this thread relief and thinking, sure, if I use a DNMG turning insert 55-degree diamond, I can just run it down the backside of that 45-degree chamfer and make this whole groove with the insert. However, I think I will use the groove tool, since it's going to be in play anyway, and just make a little relief, clear that stuff out before the DNMG comes in and finishes that up. So process number 3 will be the groove. Process number 4, I can now, let's just go in and do the finishing turn so that I can skim all of this out, bring these diameters into final. Then I will run the threading tool. And because I know just from having done this 500,000 times that if I finish and then thread, the threading tool is going to roll some burrs in and out. So what I like to do is after finish turn and thread, I'll come back in and do a little deburring action. So what I'll do is I'll take that DNMG and I'll run it up the face of this to take care of any burrs that the threading tool rolled forward, and then I will redo this back groove so that the burrs that were rolled this way will go away. However, wouldn't you know it, I think there's 2 R's in deburr. What do you think? I'm going to go ahead and put 2 in there, and if I'm wrong, somebody's going to hit me. The grammar Nazis will get me. After I deburr that thread, there's a pretty good chance that that tool will have rolled the burr back into our thread, which is more detrimental than having just a burr hanging outside the thread. So I will also rerun the threading tool through there just to make sure that my lead is not boogered. After I've done my rethread, let's go on and do our it looks like we're onto our bore now, because we have finished all of these diameters, we've rolled the groove, we've threaded, we've turned and finished, we've run this, we've deburred the thread. So now we're on to our boring cycle, which will take care of this, the counter bore, the chamfer, and finish the 750 ID. And now that's the completed part right up to a cutoff process. So now I have a rough idea of how I want to do this. Again, face and turn. Then we're going to drill. Then we'll lay in the grooves. Then we'll do a finish turn. Thread this. Deburr the thread. Rethread it. Run the boring bar. And cut it off. Sound like a winner? I think we're doing well so far. So now that I have all my processes, I'm ready to create a tool list. I have a nice little form here again, but of course a piece of scratch paper is going to work just fine. Or you can just populate your turret on the fly as you're doing this. There is no wrong way as long as you get get a good result. Boy, how many times is Charlie going to say that today? Quite a few. So let's start with station and offset. I want to have this information ready to go. Not only is this going to help me when I'm setting up the machine, but also if I hand this job off to someone who's going to run the part, they'll also be able to just look at the tool list and say, oh hey, my tool that's in station 4 needs an adjustment. Which offset is it? Boom, it's right there. So let's just go through and make this happen. Number 1, the rough turning process. Let's go ahead and stick him in station number 1 here. We're just going to say that that's going to be a CNMG turning tool, and let's give it a 15.6 nose radius. This is going to be important later on because I'm going to have to put the nose radius compensation in my offset page, but let's go ahead and say, all right, CNMG 15.6 nose and that's going to be offset 1 for station number 1. Now, I like to, when I'm strategizing my turret layout, I like to keep all of the stick tools together and all of the ID working tools, the ones that'll stick out from the face of the turret, together and grouped as far apart as possible. If you're using a 3-jaw chuck and you're trying to use a turning tool right next to a drill or a boring bar, you can have some interference issues, and we want to avoid that like the plague. But station number 2, let's go ahead and put our finish turning tool on there. So we're going to call that a DNMG finish turn, and let's also give him a 15/6 nose radius, just because I want to keep my finish nice. And yeah, there's no feature on there that really requires a 8/1000 nose radius. So that DNMG is going to be for offset 2. Now for station number 3, let's do our threading tool. Again, my strategy here is not necessarily following the process list, but it is following the OD working versus the ID working tools. So this is going to be a single point thread, thread 60 degree. This is not a an Acme thread, so I'll just go ahead and call it a 60 degree threading tool. Whoa, thread? Pay attention. Thread 60 degree, and this is, by the way, we're going to call this the single point. Keep in mind there are a million different threading tools, profile, semi-profile, full profile, We're just going to make this a standard 60 degree single point, so we don't need to incur the wrath of the tooling manufacturers by using their tools incorrectly. Okay, station number 4, let's go ahead and throw in our OD groove tool, and this one has to be, I'm going for a standard 093.5 because that will give me my big groove that's in the front of the part. Let's bring our print in here so that you can see it. It will do the groove that's in the front of the part, but it will also give us the ability to do this one. Now, as you recall, this groove is larger than 093, but that's okay because I want to use a can cycle to step the tool over and make that full part. So we'll call that an 093.5, and now we can move on to, looks like we got a turn, we got a groove, we got a finish, we got the thread. So now let's put our drill in here, but again, I'm going to skip a couple of stations just so that I don't have interference issues between my stick tools and the excuse me, the outside tools. So let's run all the way up to number 7, and this is going to be a drill. It's, let's make it a 745 insert drill, and it's offset number 7. Give it a little space just so that we keep our form looking nice and tidy. And the last thing we need is a boring bar. Let's make that one 1/2 inch because I want it to be smaller than the drill size, obviously, otherwise it's not going to fit in my hole. And now all I'm down to do is the cutoff tool. Now this is just a Charlieism, the fact that I put this all the way in station 12. I've just found that it works for me that station 1, a roughing CNMG, almost never gets pulled out of the machine. You're going to use it on just about every part. And the cutoff blade also rarely comes out. By making them 12 and 1, it just works for me. Feel free to make them 1 and 2. This is simply what works for me, as now I automatically know that my cutoff is going to be in station number 12. So now I have my tool list, but I am going to do something a little special here. On this groove tool, I want the ability to control the width of this thing. Since I'm using a single tool to plunge in, if the width of this groove isn't quite right, If I don't do something special right now, I will have no control over that. I'll be able to move the location by shifting the Z offset of the tool, but I won't be able to widen or narrow this groove. And if it turns out it's a tight tolerance, that could be a deal breaker. So what I'm going to do on my OD groove tool, right now it's set to offset 4, I'm going to say and 24. So I'm going to use 2 different offsets for the same tool, one for the front edge of the tool, one for the back edge of the tool. And you'll see when we get into writing the program that we can use that. So now we have not only adjustment for diameter and location, but also width of the groove. Very clever little trick. So now we have our tool list, our process list, and we're ready to move over to the machine. All right, so now we're out at our machine. And I'll go ahead and move over to my collision avoidance to show you that I've already populated my turret. There are my stick tools and my ID working tools. Just as I strategized earlier, I've got plenty of clearance between these stick tools versus these guys. So this will kind of illustrate what I was talking about. If this guy, this drill, were right next to this stick tool while using it, I would have to worry about this making contact with the jaws of my chuck right here. My part's sticking out far enough so to where it probably wouldn't be an issue, but I just want to be sure. Plus, this same setup is going to be used a little later on in the more advanced class when I start doing live tooling. So this clearance will be a little bit more of an issue down the road. But for right now, I know that I'm nice and safe. I don't have to worry about anything. I have already taken the time to touch off my tools. Let's go over to our tool data page. I went ahead and populated all of my offsets simply because the simulator doesn't do a very good job of showing the process of touching off tools. We're going to assume that we've already got that down to a science. But what I do have to do is I want to go through and I want to populate my nose radiuses. Tool number 1, we already know that that has a 15/6 nose radius. So here in my nose radius compensation column, I want to make sure that I put in the exact radius of the tool in both the X and the Z column. Now, some of the other lesser machines only have one column for nose radius, but Okuma does not want to assume that this nose radius wears evenly, so it gives you two different columns for this nose radius. Make sure you put the same value in both. And the strategy behind wanting to put in a nose radius compensation versus making a program with that automatically compensates for the tool nose radius is what happens if the second time we set this up we decide we don't have any 15/6 nose radiuses in stock and we have to use a Mo 31.2. I want to be able to use the same program without having to modify it. So I'm going to allow the machine to compensate for the nose radius. So there's my my roughing tool nose radius, and I do have to populate the P. Now, for some of the people that have been using FANUC controls, they use the letter T, but it's the same concept. I just opened up the manual just to illustrate what we're talking about here. We are expressing to the machine how the tool is being held. Let me reduce that size a little bit so you can see what I'm talking about. So this is right out of the Okuma programming manual for an LB style machine. And you'll notice that this is the imaginary nose radius, and that center point is the theoretical gauging point. So if I were to touch off a tool, I would get an X and a Z, and those 2 points will intersect right at that center. However, the nose radius of the tool, the actual cutting point of the tool, needs to be compensated. So there are 9 different P numbers that I could put in here, but for the sake of 2-axis turning, there really only are 2 that I'll be using unless I start doing some back turning, which is not the case in this demo. So I have P3, and as you can tell by the way that's set up, that will be for a turning tool, and the P2, that is for a boring bar. So let's just worry about those 2 right now. Since this is a turning tool, I want to make sure that my P number over here is set to 3 because that's a turning tool. Let's go ahead and get rid of this guy, and let's look at number 2, which is also a 15. Whoops, I don't think I changed it. There we go. This is also a 15.6 by 15.6. It's also a turning tool, so it'll be P3. Our number 4, our OD groove tool, there's not really a significant nose radius to worry about on this one, and so we'll just leave that blank. I don't really need to populate it if it's not necessary. And my single point threading tool obviously won't need it either. The last one, number 8, this one is going to be a boring bar of 8 thousandths because I'm roughing and finishing with the same tool, so let's make that a nice tight 8 thousandths. And because this one is a boring bar, not a turning tool, this will be P2 instead of P3. And again, our part off tool, the last tool being used, it's not necessary to have anything in there. So now my turret is populated and all of my offsets have been calculated using a touch setter or a manual method, but we're all set and ready to go. So now all that's left to do is mount our material. So let's go ahead and move this guy around. There we have, we're assuming we've got a slug of 2 3/4 inch material. I've pocketed some jaws so that this fits in nicely, and there's enough per blank that I can make the part off at the width or at the overall length of the part. Just for those of you that have a P300 control, I'd like to show you that we do have the ability to see our blank in the graphics. So what I did is from my main operating screen, I went to my Spindle 1 Setup tab, and this blank ID gives me the ability to display the material. Right now it's grayed out. I can't enter anything here unless I come down to above F6 and hit the edit parameter, and now it's whitened up. And I'm able to put in the outside diameter of the part, the outside length, so my slugs are 4 inches long, 2 3/4 diameter, and my program 0 position. Okuma likes to use the base of the part as a datum, so I have to express where my program 0 point is as the same amount as the program length. That will move the datum from the left side of the part to the right side of the part. Sometimes I like to make that a little bit shorter. Let's just give it 10 thousandths. It's not going to change the way the machine behaves at all, but what it is going to do, it will show in my graphics a piece of the material coming off the face of the part. It's handy to see. Now if I say OK, it'll ask me, do I save it? Yes, I do. And now it creates a data model, and I'm all set and ready to go. Time to start programming. Is anybody going to call me on something I missed? Yeah, I'm going to. I have not set my 0 offset yet. That is the point of the material, the face where my 0 point is going to be. The end of the material is my datum, so I need to express that to the machine. There are several ways of doing this, and I'm going to talk about 2 of the most popular right now. The first is if your tool setter is calibrated with one of these tools, any one tool, having a Z offset of 0. If that's the case, then all we need to do is to call up that tool. So we'll put tool number 1 in the cutting position. Let me rotate this around so that we can see whether or not it's there. Yep, there it is. There's my tool number 1. It's in the cutting position. So now I can jog my machine up to the face of the material. Now, because I'm using collision avoidance, I know that, hey, it says, oh, you need to stop right there. But with a standard machine, now that I've got the tool number 1, the 0 offset tool in the cutting position, I could light off the spindle and make a facing cut across the face of the part, or touch the face of the part if it's already a finished datum. Either way, I want to make sure I don't move my Z from its current position. Now if I come back to my main operating screen, I'm still in the Spindle 1 Setup tab, and 0 offset is currently grayed out. So by using F5, 0 edit on and off, when I touch it, it opens up, unlocks the 0 offset. And you notice that it moved the cursor right to the Z axis because Okuma knows that this is the main function that I'll be doing anytime I move my 0 offset. The X0 should remain at 0 all the time if your machine has been calibrated properly and not bumped or knocked around. So we'll almost never adjust that guy right there. But my Z, because the machine is currently sitting right where it belongs, I can simply touch the calibrate button and use an integer that represents how far from my current position is the Z going to be. In this case, it's 0, but that's because I made a facing cut. Let's say, for instance, I touched off of a 1-inch side of a 1, 2, 3 block. I would say that now currently I am sitting 1 inch away from my 0, and then pushing input will update the 0 offset. 0 input, there's my new 0 position. The second way that I alluded to of doing this is if your tool setter has not been calibrated with one of these offsets as being 0. If I touched all of my tools and all of them have a value here, now I have to be a little more careful with my process. In MDI, I'm going to call up one tool, any tool that I want. In this case, let's use tool number 2. And because I am doing something funky, I want to make sure that I call up that tool in MDI. Let's go caps lock with that. T0202, enter and cycle slam. And now tool 2, oops, it didn't move. Let's, boom, there we go. Now it's in position. I'm coming back over to my main operating screen because before we get too deep into this process, I want to make sure that I show you guys the potential bite you in the rear end that's going to occur here. You notice that here on the bottom of my screen it shows that tool 2 and offset 2 are in the cutting position and the offset has been read. Let's go ahead and look at my machine graphic right there and tip it over to the side a bit. There we go. Now I have to move the tool over to the face of the part, but here's where people make a mistake right off the bat. You know that right now if I try to move my machine, it won't go because I'm in MDI mode. Oh, I need to be in manual mode, but watch what happens to my tool and offset when I switch over to manual. It dumps the offset. So this is where you have to keep your head in the right position. T0202, we'll do that again. Execute, now it's in position. Don't go out of MDI. So how in the world do I move my machine if I don't get out of MDI? Okuma has this button right here. Some of you use it, some of you have never seen it before. This is awesome. Mid auto manual. If I turn that on, now I can jog the machine even though I'm in MDI mode, not manual. And my offset's still active. So now I can move over and make the process exactly as you saw me do just a minute ago. I want to run to the front of the part, make a facing cut, and then come to my spindle 1 setup and do calibrate 0 input, and now my number is good. But before I ever hit the calibrate, I always make a point of going back to the operating screen and make sure that my offset is still active. Otherwise, the number that I get is going to be incorrect by whatever value is in my z-axis. Clear as mud, right? I'm going to hit reset now, and now my offset's dumped, and I can get the tool back out of the way. All right, so now my work 0 is set, my tool offsets are all set, and now I really am ready to go into the programming stage. So the first step we want to do is find the Program Operations button on our key panel and press it, and it will show us the machine directory 1 by default. We'll call it MD1 throughout the duration of this class, but just know that it stands for the machine directory, the primary, number 1. Some of you that have Advanced One Touch installed on your Turning Center, you'll see these 2 tabs in the upper right hand corner of the screen, one for NC Program and one is for IGF or AOT graphic files. I do suggest that you want to make sure that if you do have AOT installed, that you touch the NC Program tab and make sure that we are looking at the MD1. They have another name for the IGF folder. It's just another directory. And if you maintain this AD0 as being all of your graphics files for AOT and all of your handwritten NC code in MD1, by keeping them separated like that, it makes life a little easier when you go looking for a specific type of file. So I'm ready to create the file. If you'll notice, the soft key F3 is listed as new file. By touching that, I get a new option down on my soft keys to create a directory, which is, it's just a Windows style folder so that I can categorize the program if I want to. You know, I could heap all of one customer in one folder, another in another, or by rev numbers. Sky's the limit. Use it however you like, but what we're doing is we're just creating a new NC program. So as soon as I touch the NC program key, now it comes up with the question, what is my file name going to be? I'm going to call this, oops, better have caps lock on. I'm going to call this class. I do not have to add the .min, it will bring that in by default. But I do want to take this opportunity to show you a mistake that's made by just about everybody, including myself, at least once in a while. Here is the name that I just typed in, class. By default, the file name of a new file is a.min. If I fail to hit the input key after typing in the word class, and I just get distracted by this OK button above F7, when I hit it, it creates a program called a.min. Once I finish with this thing, I won't be able to find it because I thought I named it class, but the machine did not accept the class input, so it created a.min. How do you get around that? Type in your program name and then make sure that you hit the input key. And now you notice that it took the word class from my input buffer and put it into the file name field up here. Now when I click on OK, it's created the program called MD1 class. That mistake gets made an awful lot, so let's just keep our eyes out for it. So now we have a blank screen where we're ready to start programming. I'm going to click over to the look inside my machine to show you that this particular simulator has 2 spindles, which means I have to start the program with a special code. I have to specify which spindle I'm working on. G140. That means left spindle. Right spindle would be G141. If you only have a single spindle machine, don't worry about this code. It's not something that you need. But if you don't put that in on a standard two spindle machine, it will give you an alarm right off the bat saying, hey, I don't know which spindle I'm working on. You better specify. It is, oh, come on, I put it on here somewhere, didn't I? Nope, I omitted it from the G code list simply because I figured we were working on a 2-axis. So it's not listed on your form yet. Okay, so that is going to be the very first line. Now, some of you that have some programming experience with other brand controls will go, hey, what happened to the usual stuff that I used to have to type, like 1, 2, 3, 4, or even more aged than that? What about the old percent sign or the dollar sign or one of those other characters that we used to have to put in? Here's a little thing for you. If you are not communicating with an RS-232 wire, then you don't need any of these little preamble characters like the percent or the dollar sign. And since my machine has USB and Ethernet capability, I'm never going to use RS-232. I'm going to omit that. How about the O number? That's also not necessary. Other brands of controls require that as the identifier for the program that we're currently working on. But since we are Windows backed, it already knows the name of the program right here. Instead of going by a number, it is referred to as class.min. So I don't need an O number. I can have it if I want to, but it's certainly not necessary. I just don't even look for those anymore. Second line of code that we're going to put in here is it's a graphics related word. Clear and draw. These are also not required, but since we're writing this at the control and we don't have the benefit of a CAM system to show us any errors, we're going to want to utilize the 3D graphics function on our machine. I want to know what's going to happen long before the tool actually touches metal. So the clear and draw statement that's in the header of this program are going to do exactly what they say. Clear is going to erase the trace lines and the previous material drawing in the 3D graphics, and the word draw is going to return the material to its solid form, the original form that it had before we started cutting. The next code that I want to do is right here on my list. I have to specify, have to specify to the machine what is the maximum spindle RPM that this setup is capable of achieving. Now, a bunch of people out there are going to go, well, heck, it's a 4,500 RPM spindle. I want to go 4,500 RPM. That's fine, but as you saw in my setup, I have a 3-jaw chuck with a 2 3/4 inch chunk of steel sitting in pie jaws. In fact, they're not even pie jaws, they're just standard jaws. So, you know what? I really don't want to be doing 4,500 RPM. So I'm going to utilize this code right here, G50 maximum spindle RPM, G50, and I'm going to put in the RPM that is the maximum I feel comfortable with this setup. Let's just say OS 2750. Depending on your setup, yours will obviously be different, but hey, that's good enough for me. That'll keep the keep me from scaring the snot out of myself when this thing ramps up to go across center line. And the last thing I want to do in the creation of the program is I want to make sure I put in the home command. I want to send the turret from wherever it is to a safe position. I always put this in the header of my program simply because I have no way of knowing where the turret was or is when I hit cycle start. So I just want to make sure that I have a safety net. No matter what happens, when I hit cycle start, the first thing that occurs is the turret goes to a safe position. If you have programming experience on some of the other controls, they have, a couple of fancy little G codes and, special functions. Go to this home position, and yeah, Okuma doesn't even bother with making you learn something new. G0 for rapid, X30. That's close enough. By specifying a travel command in rapid mode that is greater than the travel of the machine, Okuma just assumes that, okay, you mean go as far as I can go and then stop. Obviously, a machine the size of the one you see me working on here doesn't have a full 30 inches of X travel, but the control looks at the command and says, gotcha, we're in rapid mode, so I'll go to my stops and then be done with it. And let's move Z at the same time so that both of them will go to their full position. I only put Z10 here, even though the machine I'm working on has more than 10 inches of travel. Only one axis needs to be at the stop. On a twin spindle machine, that is the X-axis, and I see right here that, yeah, okay, that's going to position it up against the stop, and that's going to position the turret 10 inches away from the end of my material. That should be plenty safe for the turret to index without actually clipping the material. One other thing that I'd like to point out on this, you notice I didn't put a decimal place in here. I did not bother to say X30 point, Z10 point. It doesn't matter if I have the decimal or not. If I omit it, Okuma assumes that that's a whole number. On some of the other controls, if you omit the decimal, it looks to the far right digit as being the tenths digit and the second as being the thousandths. So on some controls, that command means to go to X3000s. Oh geez, that's confusing as all get out. Okuma, no decimal, all right, it's a whole number. So I could say X30 point or X30 and it means exactly the same thing. Same thing with the Z. And as long as I'm talking about it, I'd also like to demonstrate that I don't have to have spaces in between these. I'm putting it in there for the sake of this class, but if I'm in a hurry or I just don't want to reach down and hit the space bar, I can cram these all together. The only stipulation is, the only time you have to have a space, let me put it that way, is if the first statement ends in a letter. Whoa, I can't even give you an example of that. The proper way, if the first statement ends in a number and the second one starts with a letter, then we're fine. So X30, obviously that ends with a number, and Z10 starts with a letter, so it's perfectly okay to back up and put those two together. All right, so now we've created the header of the program and we are ready to move on and start making some cuts. Now this header that I wrote up above is pretty generic. I'll use the same header for just about every program, and I'll throw in some extra codes like that G140 if I've got two spindles, or the G code to command upper or lower turret if I've got a multi-turret machine. But for the most part, that's all I will put in for the header of the program. I'd like to take this opportunity to give a little asterisk on here and let you know that there really is no wrong way to create a header. Same thing with the tool call that we're about to make. There's no wrong way to do it, but I have a set pattern that I've memorized that I use every time I'm writing a program by hand so that I know I don't miss things. Feel free to adopt what I'm doing, but if you already have a header in your mind or you find one that works for you, just stick with it. That's my key. There is no wrong way of doing things as long as you get a good result at the end of the day. And I'll probably say that about 20 more times before the end of this class, but seriously, if you get a good result, there is no wrong way to do things. I get an awful lot of flack on my YouTube channel from people saying, oh no, you shouldn't do it that way, you should do it this way. Fine. everybody's got their opinion, but at the end of the day, if you made a part and it checks good and the cosmetically it's in, dimensionally it's in, you won. So don't stress over your semantics being different from mine. Just use what works. And so that being said, I'm going to show you what I use each and every time I try to call a tool. I like to start with a sequence name, and that's an N. The letter N is going to represent a sequence name regardless of what follows it. The digits that follow the N number are simply an address that you can use to find a certain tool or a certain process or a certain way of doing things. Some of the other brands of control restrict you to numbers after the N. Okuma doesn't do that. You can use letters and numbers combined to make something that is logical to you. For instance, we're about to do a turning process, so it's perfectly okay for me to call this N turn or N drill or N tap. I can do pretty much anything that makes sense to me, and that's really handy. Particularly if I'm trying to put a sequence in someone else's program for troubleshooting. If they haven't got a sequence right where I need it, I'll just add one that I know won't confuse them, like N here. That's my favorite one, H-E-R-E, N here. You have any 4 digits after the N to use as an address that makes sense to you. You can also incorporate numbers in there, but just know that in the sequence, once you've shifted to numbers, you can't go back to letters. It is okay for me to say N tap 1, but it's not okay for me to say N1 tap. That will cause problems. So that being said, what I like to do is to use a number that corresponds with the tool number that I'm using. On our process plan that, let me see, I've got it right here. Oh, there it is. So the first item on our process plan is the turning tool, and from our tool list we know that that tool is tool number 1. So for our sequence we'll call it N1. And now I want to put in a series of modal codes that are going to basically put the machine in a status that I am comfortable with. And again, I always use the same sequence just so that I don't miss something. The first that I always use is G0. There's a couple of reasons. For one, just before I started this sequence, I sent the turret home. Therefore, the first thing it's going to need to do in order to get ready to cut something is to position itself, and G0 is the rapid positioning call. G0 will cancel cancel any kind of drilling cycle, any kind of can cycle that might have been active. Now, Okuma is really good about canceling these cycles for us when we hit reset, but that's another function of G0 that I like to have in there. The second code I always use is to explain to the machine which feed mode I'm using. If I come back over here and I look at my G9596, this is explaining whether I'm using my feed expressed as a distance per revolution of the spindle, or it is the feed per minute, inches per minute feed rate. So this being a 2-axis, and we're not doing any kind of milling because, hey, 2-axis does not imply milling. I'm going to use G95 so that the feed rate that I express is going to be the actual chip load that the tool is pushing. So now I have G0 and G95. The next code that I always put in is G97, which, going back to our little list here, G97 is constant spindle speed command, which means whatever spindle RPM I dictate right here is exactly what the machine is going to achieve rather than G96, which means the machine is going to calculate where the tooltip is right now and spin the RPM to achieve the surface feet per minute that I've specified in a G96. Wow. Boy, I hope he explains that better in 5 minutes. Yeah, sure I will. G97, and now I'm going to put in a directional command and S1000 just to get the spindle turning. So my first line in this modal cycle is N1 sequence, rapid. We're going to use feet per minute, G97 constant spindle speed clockwise at 1000 RPM. Now my spindle is turning. The next thing I'm going to do is I'm going to repeat that sequence number. Same one right here. This is not something I do on older machines because it's extra, but on the modern Okumas, there's a feature on it called Tool Restart, and that Tool Restart will show you when we go into the verification of the program. Once the program is entirely written, I'll show you how to use the Tool Restart function, and it just makes life really easy because, oh hey, I want to restart at the threading tool. We'll go to a page and say that's where I want you to start. You don't have to remember any sequence numbers. The whole reason I went into that big explanation is because that Tool Restart function requires you to have the N number on the same line as the tool call, which is what I'm about to do. So N1 repeated, and now I'm going to call up tool number 1. But that is not a complete statement here, because the T command requires not only that we tell it what tool number or turret position, but it also wants to know which offset we're using. So in 4-digit format, the first 2 digits are representing the physical turret position. The last 2 digits are the X and Z offset that we're going to use for that particular tool. On a machine like this that's 2-axis, they're almost always going to be the same. There's no reason to complicate it by saying something like, tool 1 offset 21. We are going to do that just to show you how it works a little later on, but tool 1 offset 1. That is what most of the other brand lathe programmers know as the tool call format. But Okuma guys will see an extra 2 digits. Whoa, wait a second. Now we've got 6. If you're using the 6-digit format, the first 2 digits are the nose radius compensation for that tool. Second 2 are the turret position, third 2 are the X and Z offset. So anytime you intend to use a G41 or G42 in your program, make sure that you've called up 6 digits, not 4. The machine will take either 6 or 4 if you're not using G41, but if you only have 4-digit and you try to command G41, the machine will alarm out saying, hey, I'm not going to assume that this is the nose radius compensation value that you want. So now that I've told it we're using tool number 1, now is a really good time to put an operator note in there to explain to the operator what this tool is. CNMG rough turn. For those of you that aren't really versed in CNC programming, anytime I put anything in between parentheses, the machine doesn't read it, skips it right over. It understands that that is just a note for whoever's reading the program. In this case, that's us. So now I know that tool 1 offset 1 nose radius comp 1 is the CNMG rough turn. Last thing for this line is going to be an M8. Turn on the coolant. That's kind of important. So now my spindle is turning, my tool is in the cutting position, and my coolant is on. I'm ready to move from where I am now all the way up in the stop position down to an approach point on the part. Some people I've seen will write a program where they just zip right into the cut. I mean, they'll wrap it from this point right down to the face of the part. And if you're in production, that's fine. Knock yourself out. However, it always scares the bejeebies out of me because I want to see an intermediate point, something that the machine is going to go to prior to touching material, so I have one last chance to see whether or not my tool is gauged properly. So let's give that an X value, and we know that our material is 2.75, so I'm going to tell it to go to 2.85. That is a diametrical value, so as I'm looking at the machine, I'll see that the tool should stop 50 thousandths radially from the OD of the part. And I also like to put in 100 thousandths in Z so that it will position that tool roughly, 100 thousandths by 50 thousandths from the edge of my rough material. And so if I'm running in single block, I can let this thing come down and park at that position, and then I know, yeah, okay, my tool is gauged properly. If it goes beyond that point or doesn't quite reach that point, I have a warning that, hey, I screwed something up before the machine moves on and makes a mess. One thing I skipped over, you notice that I've been adding these little arrow down here. If you are a programmer of some of the other controls, you're probably looking for the EOB key, or end of block key. On those other controls, when you push that key, the code types in a semicolon, one of those little guys. Okuma doesn't use that. We don't need to. By stroking the input key, it'll automatically put in this ASCII character that means carriage return line feed. There is no arrow key on your machine, but that enter button or the input button will generate that code for you. And when you're done typing, just push input. All right, one last piece of information that I want to use for the tool call. In this particular case, we're doing a turning tool, and I haven't really specified the material, but I'm going to call it 4140. Just to say I did. I don't want to get into splitting hairs about, oh, your feeds and speeds are wrong for 4140 or this. No. We're not going to try to deal with feasibility here. We're just going to say, hey, this is steel. And because this is steel, I do not want the tool to work harder than it has to. Remember, we talked about this G97 right here, which turns on the spindle at 1000 RPM and it'll just leave it there. That's all well and good if I were drilling, but in this case, the tool, as it gets closer to the center of rotation, is going to contact material at a slower surface feet per minute than it would if it were further out. The machine knows that that's not good for a tool, so it gives us a cycle where we can specify a surface feet per minute, and it will change the RPM for us in order to maintain that surface footage based on where the tool tip is. It's doing the calculation for us. It's really cool. So in my case, G96 now is constant surface speed, and I want to put in an S and specify what the manufacturer's recommendation is for this tool in this material. So 4140 for this tool, let's just say, is 650 surface feet per minute. So now the machine will have shifted from constant spindle 1000 RPM to constant surface 650. And that, with the exception of adding or subtracting this G96, is the format that I'll be using for every one of my tool calls, and I just have it memorized so that I can spit that stuff out in my sleep. Now we're ready to move on to physical cutting. So let's swing our print back in here and take a look at what we decided. So our first process in just about every part I do is to run the roughing tool across the face of the part to establish a datum. We're going to be drilling here in a few minutes, and if this happened to be a saw cut piece of material or something ugly, I don't want to try to drill or put some kind of fragile tool on a rough surface. So I'm going to swing my roughing tool from the position where it is now, right about where you see my cursor. And the first thing I want to do is move to the face of the part, and then I will feed down over the center line, pull it back out, and return to that position. So let's just do that one step at a time. We already know that we're 100 thousandths away from the part at above the material diameter. So the first thing I'm going to do is to say, I'm in rapid mode right now. So I'm going to move, let's just say 2 thousandths off the face of the part. Since this is a roughing tool, I do want my finish tool to take a little bit of material, but the Z in general does not like to take a lot of material. So we'll just give it 2 thousandths and be happy with that. Now that was a rapid positioning move, which was fine because I'm up above the material, but now I want to go into feed mode before I move things down across the face. So G1, taken right from my G-code list, right there, linear positioning or interpolating. So now I'm going to G1, and I want to move down in X over the center line so that I don't leave any abnormality right in the center of the part. So let's specify that this is moving in the X-axis, and we'll go minus since we know the center of the part is 0. We want to go beyond that by at least the radius of the tool, but in my case I usually do a little more than twice the radius just to make sure that everything's cleaned up, it's gone over the center line. So now I've moved in quickly, fed down. I haven't specified a feed rate yet, so let's go ahead and give it, I'll say 6 thousandths. That should be enough to not abuse the tool, but definitely I don't want to spend a lot of time on this cut because it's just a roughing cut. Now I've moved beyond the center line. The next thing I want to do is get away from the material. Now I'm doing this in feed mode, mainly because my machine tool here has collision avoidance software and it does not like to move to rapid mode when you are touching material. So I just fed back out. I can do that extra fast since we're not cutting anything, but now I've moved back out to 100 thousandths, a nice clearance plane above my material. Now I can shift back into the rapid mode and go back to my 2.85 clearance diameter. So now I've just zipped across the face, moved back out, and cleared the part. Let's go ahead and verify that. You know, I've already made motion, so let's go start our graphic verification process. Before I get out of this program though, I'm going to want to put in one more code that represents end of program. Obviously I've got a lot more to do, but anytime I want to run this program, I have to have an M2 or M30 to signify to the machine that that's the end of the program, and I want you to stop everything. All right, so let's go ahead, and I'm going to push the quit stop button here. Because I've made a change to my program, it says, hey, I just did some editing. Do you want to save it? Yes, I do. Now, let's get rid of my print here so I can see my keypad. I'm going to go to my automatic mode, which takes me right to my main operating screen. Now this isn't going to help me any to view the process, so I'm going to look at my special functions graphics page. If you have an older control, you'll see right on the front here a display change button. On the newer P300A controls, you'll have to arrow over one time, but then you'll find display change, and by touching that I get a window that pops up that shows me all of the different available screens that I can look at. Some of you may see an abbreviated version of this screen. I have the ability to filter out ones that I'm not using. Let's show you how to do that very quickly here. With this window up, if I push the arrow over button, F1 will change into a value of menu change. By touching that, it allows me to say, yeah, I don't want to see that, I don't want to see that, I don't want to see that. The one I do want is animated simulation. So now I've abbreviated my list somewhat, but I just want to pick up animated simulation and then close this outer window. There's my graphics. And now I'm just, before I do anything else, I also want to make sure that the machine can't move. Obviously, it would be very bad at this point, since I haven't proven anything, if the machine physically, indexed to tool number 1 and went down and made a facing cut. I'm not ready for that yet. So what I'm going to do is I'm going to basically build a wall in between the computer and the machine by using this button right here, Machine Lock. On your keypad, you'll notice that Machine Lock is one of the few that's white. All of the other membrane panel buttons are a different color. A white button indicates that you must press and hold the IL or interlock release button to engage the specific button that you're trying to access. So I push and hold the interlock release button, and then I push Machine Lock, and now the computer is separated from the machine, and I will be able to see the graphics run, but the machine itself won't run. So let's go ahead and turn on single block so that I can talk while I'm doing this. It means that every time I hit the green button, it's going to execute one line of code. And one more thing I want to look at, in my graphics, it's showing me distance to go and feed rates and velocity and cutting time, but it's not showing me the program. I want the program. So I look down here, and the value of soft key F5 is program on and off. If I touch that, now I get to see my program. Every time I push cycle start, we're going to see it go through one more line of code. There's the first one. Now it cleared out the previous graphics. We didn't have any, so you didn't see them go. Push green one more time, and now it drew my material for me. Dynamite. And touch it again. Now the RPM limit has been engaged. The machine has gone all the way home, and in my case, oh, hey, collision block. Let me fix that. Okay, I fixed it behind the scenes because, well, doggone it, you guys don't need to worry about my simulator thing. Okay, so let's turn back on my program, and I hit cycle slam. There, it cleared the old graphics, drew the new graphics, went home. Now on this line, it took my modal codes and started the spindle rotating. Then it called up tool number 1, rapided to my clearance plane, and now it's going to shift into a constant surface speed, move to Z 2,000ths off the face of the part, and now I'm going to see a facing cut go down the front of the part. Let's go ahead and crank up my my feed rate and my spindle RPM to make it go faster. Next move, it's going to move to 100,000ths away from the material and rapid all the way up to my outer position. Dynamite. Now, one thing I didn't show you that I probably should have, but before I go and run this, I should main program operate, program select, and pick up the program that I was running. There it is. If you, we're going to see in just a minute a way to compress that operation with finishing our editing function, but I just wanted to get that out of the way. Now let's run through it. Whoa. Look at what I did. Unusable directory. How come nobody busted me for this? Can you tell what mistake I made? G0 2.85. There's something missing there. Get back in and edit my program. There it is right there. G0 2.85 in what axis? I forgot to put the X in there. Yeah, now it should be all better. But now that I brought that up, let me show you that feature that I was just talking about. I made an edit change. Previously, I used the quit stop function. If you arrow over one time and use select and quit, instead of just saving the program, it also reloaded into the OSP the modified program. So now if I run it again, let's take off single block and just let it go. There's my X that caused the problem previously. Done. All right, so now we've graphically verified that our facing cut is functional, and we're ready to move on to the next item. Now, as I was doing this cycle, or this cut, that tool was only pushing a few thousandths off the face of the part. It was not an extreme amount, probably a maximum of 20 to 30 thousandths, which the tool can handle without any kind of issue. However, my next cut is going to be roughing out the periphery, the OD of this part, and that is not a true statement when I'm bringing the tool across the face. Sure, up here there's a minimum amount of material coming off, but as I get here there's more material here, so I have to do something other than just trace the tool over the OD of the part. Sure, it may work for some parts, but it certainly is not the case for this one, as this diameter, the 1.5, is well below the 2.750 that the material measures to start, and that's just too much for my tool to push. So I need some assistance from Okuma on this. And what we're going to do is utilize a canned cycle. I'm sure you've heard that phrase used a whole bunch, but let's explain what a canned cycle is. If I would like one of my kids to go get me a glass of water, I can just say, hey, I'm thirsty, will you please go get me a glass of water? I don't have to tell them, I would like you to pause the PS3, get up off the couch, walk across the kitchen floor, enter the kitchen, open the open the cupboard, pull out a glass, put it under the faucet, lift the faucet, da 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 da. I'm able to say simply, hey, I'm thirsty, would you please get me a glass of water? And I can trust that the process is already clear in their brain, and just a few parameters that I give them: water, glass, thirsty, and they can fill in the rest. Well, it's the same thing with the machine tool. With a canned cycle, that's the equivalent of asking the machine, hey, I'd like you to do something, and I'd like you to do it with these parameters, and go. So the canned cycle for doing roughing is G85. I've opened up the G85 cycle in the document package, and I have my step-by-step instructions here, an example of utilizing the instructions, and also the page of the manual that shows exactly how what parameters the canned cycle's looking for. So let's go ahead and open up our program again. We're going to push the program operations button, and it will take us back to the machine directory 1. Our class.min is still highlighted and it's blinking, signifying it's the active program. By touching edit, it will open up that program, and we'll position the cursor right after the facing move that we just made. Now we can come over here to our roughing canned cycle document, and let's make sure that all of the conditions for utilizing this have been satisfied. Move tool to clearance plane, that was done right there at the previous, before the facing cut. Put tool in cutting position, there it is. Spindle commands, we know we did that. Coolant, move part to clearance plane. Now the tool was moved to the clearance plane here, but then we did a bunch of stuff moving the tool around the face of the part. So I want to make sure that I have delivered the part back to the tool back to the part clearance plane. X 2.85, we know that's above the diameter of the stock, and Z.1 in front of the face of the stock. So I'm happy, and it has satisfied the move tool to part clearance plane. Number 6, call the cycle with cutting specifications and roughing speed. Hey, I'm going to skip a little space there. You don't have to. I'm just doing that in order to keep keep everything understandable. So let's call the cutting cycle, which we know is G85. That's also on my G code list right there, G85 bar roughing cycle. So there's my G85, and now I have to specify a few parameters. The first of which is a sequence that is where the first block of the contour is. In other words, the machine needs to know where am I defining the shape of the finished part. And that's going to be defined by a sequence. And as you notice right out of the manual, they like to use NAT. So I'm a big fan of that. NAT. The reason I do that is because I've been using a sequence number at the beginning of a tool, so I like to do something a little differently for shape definition, and that's pretty much why Okuma created this format 30 odd years ago. That stands for sequence A turret. So if you have a more complicated machine, you might see NBT for the B turret, but we only have one turret on this machine, so NAT is all we'll ever see. That's not that could be enough information if I were confident I was only going to do one roughing cycle in this part. I'm not. I am not confident at all. I have a roughing turning here. I'm going to have a roughing boring cycle a little later on. So let's go ahead and put a designation, a number designation on here. This is the N A turret first can cycle definition, first shape definition, NAT01. And now let's come back up here and look at, okay, we did the call cycle with cutting specifications. I am not done just by saying, hey, I'm going to rough and this is my shape, or this is where the shape is defined. I need to put some parameters in here. And those parameters are listed on this page. And while the manual puts them in this specific order, I can use any order I want as long as I include all of the mandatory information. Just about everything you see here is mandatory information. It needs to know a depth of cut, a feed rate, the stock removal and finish turning cycle. What does that mean? That's the finish allowance in X and the finish allowance in Z. This little code right at the end, the G84, is change of rough conditions. That's optional. This is only necessary if in the middle of the roughing cycle I want to change my cut conditions, like the feed rate or the speed, or it's advanced stuff that I'm not using right now, so we'll not even worry about that. Let's just worry about the mandatory information. I don't follow this this letter sequence because I'm used to doing things a certain way, and doggone it, this is just how I do it. You can put whatever you want in here, but I always start with the U, or the X finish allowance. This is the amount of material that's going to be left on the X-axis of the part during the roughing cycle. And then we've got one for W. That's the Z-axis finish allowance. And then we're going to want a depth of cut. Whoops, that's a little short. That is how much the maximum material that will be pushed by the tool is allocated right here. 300 thousandths is the maximum that the tool is going to be pushing as it moves up the axis. Now there may be a lighter cut if, say, for instance, the cut amount doesn't come out even, but it will never exceed 300 thousandths. And my last is the feed rate, and the feed rate that I put in here, just as it says right here, is in the rough turning cycle. Only this tool, the roughing tool, is going to be tied to that F.012. I'm able to specify feed rates in my shape definition that will only apply to the finish tool, and we will do that here momentarily. Let's get rid of that guy and bring back up our print so that we can go through, and now we need to define the shape of our part as specified right here. So the first line, NAT01, whoops, make that active, Charlie, NAT01. I put this in here making sure that it matches the code in the call up. Just so you know, NAT1 is different than NAT01. Make sure that these match exactly. Just as a footnote, it's not required that I put the shape definition NAT01 right after this G85 line. I can put it anywhere in the program, but because it makes the most sense to me, this G85 NAT01 call will be right before the actual shape definition. The only other piece of information that we want to put on the first line of our shape definition is the type of cut that we're using. In our case, it's G81. And a G81 is the shape pattern moving, cutting in the Z-axis, sort of like you see the cursor moving right here. It'll make the cuts in Z, and the positioning moves will be in X. If I wanted to do the opposite, where the cutting motion is in X-axis and the positioning is in Z, that would be G82. But in general, I use the G81 most often simply because I want to keep the tool in the cut the longest. I don't want the wasted moves to be the majority of the cut path. I want the physical cutting going on. If I were facing a disc, that would be more efficient to use G82, but in this case, G81 is just fine, and that's the end of the first line of our shape definition. So let's start, and the very first move that we want is to move from where the tool is now, that's right about here in our clearance plane, and we want to rapid down in X to where we're in position to start our cutting profile. And this is a mistake that an awful lot of people make. You need to understand that this first motion is how the computer is going to decide whether we're doing an ID or an OD roughing cycle. If my rapid is in X plus, then it assumes we're doing an ID cycle. If the rapid is in X minus, it assumes we're OD. And that's important because it needs to know which side of the material to leave this finish allowance. It's critical. So we are going to make a G0 motion, and we're going to go to X. We're just going to say 1.0. I don't need to go all the way down to center line because I know I've got a counter bore in here that's like 1.25 inches. So as long as my tool is down below where that material will be residing, phew, I'm in good shape. So now the tool is sitting right about here. I'm ready to kick into feed mode, G1, and move to the face of the part. But this is also a very good time to put in my tool nose radius compensation. So at the risk of over-explaining the concept, here we have 25 thousandths radius called out in the print. If I were to just program 25 thousandths and the machine swung its axes to make a 25 thousandths radius, we know that there's a 15.6 nose radius on the tool, so we would have significantly less of a radius on our part. And it would be just a pain if we had to do the math every time to say, oh, okay, 25 thousandths nose radius plus the 15.6, and that's a diametrical value. Oh, wow, that's way too confusing. Let the machine do the thinking for me. By adding this G42 nose radius compensation for OD, it will automatically compensate for the tool nose radius to cut exactly 25 thousandths nose. And then we're going to move to Z0, and since we're not cutting anything, let's go with a nice high feed rate, in this case 6 thousandths. Now the tool is sitting right here at the face of the part. We're ready to make a motion up and swing this radius. So we know that a straight line move is G1. We established that right here. And an arc move, clockwise would be G2, counterclockwise would be G3. And I have to consider this radius right here. So if I didn't have Okuma helping me out, I would have to move in a straight line to where this radius starts and then shift from G1 to G3 to throw the radius in there. But wow, that's a lot of math. I'd have to take the 1.5 minus the radius minus a radius on the other side, terminate that. Oh, what a pain in the butt. Let's go back over to our G-code process and look up automatic chamfering, automatic corner rounding, G76, G75. that's going to help me out greatly. To use this, all I need to do is tell it that I'm going to utilize the corner rounding, or the auto corner rounding cycle, which is G76. Now, instead of doing a bunch of math, I'm simply going to tell the machine what's the final diameter that I'm going to. In this case, it's X 1.5. Now I need to tell it, before you get to that 1.5, I want you to swing that radius. And that value is an L. It's for the radius or the chamfer, depending on whether you're G75 or 76, it will always be an L value that just represents how big is the radius or the chamfer. And the next thing we have to do is decide whether the L value is a negative or positive value. And the way I explain this to customers on site is that a chamfer or a radius is a two-axis move. Has to be. I mean, that's the only way you can make a chamfer or a radius, is to move two axes at the same time. So one of those two axes has been named in my statement. There it is, X. One of those axes is unnamed, in this case, Z. So my question is, which direction do I want the unnamed axis, Z, to move to properly swing this radius? If I come up here and I swing the radius, notice that the Z, or the unnamed axis, is moving in the minus direction, which means that my L is going to be negative. L minus 0.025 will now swing a Z-axis negative 25 thousandths radius before it gets to the 1.5 inch diameter. And we'll give that a feed rate. Again, the roughing is going to ignore these feeds in here. This is just for the finishing tool. So now we have moved up to our major diameter, we've swung the radius, and we're parked right here. The corner radius and corner chamfering automatic cycles are just dynamite. I use them all the time, but here are two rules that you have to observe when you're using this. First off, you have to have a straight line at least 1/10,000th of an inch before you swing the radius. It has to make a straight line. So let's use an example of what you can't do. We already know that this is a 1.5 diameter, minus 25 thousandths on this side, minus 25 thousandths on this side. So 1/450 is where this radius starts. I could not command the machine to go to 1/450 and then try to tell it to swing a 1.5 inch radius at L minus 0.025, because it would not have enough space to make that 1/10th of straight line move. It'd be just fine if I made this 1.449 and then this to 1.5, but I give it enough motion so that I can just look up there, glance at it, and say, oh yeah, there's plenty of motion. The second rule is the exact same thing on the exit of the arc. I know that this is Z0, so when the arc terminates, it'll be at Z minus 0.025. I have to have a straight line after this radius that goes further down than where the radius terminates, so it knows how to mathematically compute this, which works just fine for me because my straight line move is going to go all the way down to minus ½ inch. And let's pump that back up. Notice that I decrease my feed rate as I'm going around two axis moves just to minimize the record player look. However, if it's a single axis move, I can just haul on the thing and I'll still have a nice surface finish. So now I've zipped down to this corner right here with that Z minus 0.5 move, and I'm ready to, hey, move up to this diameter, and there's a chamfer. So this time we'll use G75, the chamfer move. And my final X diameter is the major of this thread, or X 1.995, and L, again, my unnamed axis. It's not X because X is named, so Z is going to move in the minus direction, so L minus 0.075. And we'll give that the slow feed rate again because it's the two-axis type motion. Now I'm ready to make my Z move, and it looks like Z minus 1.250 will take us down to this point right here. Now I'm ready to make this chamfer. I cannot use the G75 cycle because, as I just explained in length, I don't have any motion to make a straight line X before the start of this chamfer. So I will just say move from X 1.510 and Z, oops, did I make that mistake? I sure as heck did. That's a 2.5x, x 2.5, and the Z is minus 1.510. And let's make that at my reduced feed rate. All right, that puts us at this point. Now I need to finish off the part by saying Z minus. Now, if I just said 2.5, that would, in theory, mathematically finish the part, but it would leave a radius for the tool, right here at the end. Plus, I'm going to part this thing off. So I would just as soon have the roughing and the finishing tool continue on past this 2.5 margin by the width of the part off blade, and then I'm going to add another 20 thousandths or so to it so that I don't risk running my part off blade into a wall of trash material back here. So let's just say we're going to move to Z minus 2.645. My part off blade's an 1/8 inch, so that would be 2.625 minimum, and then add 20 thousandths to that just for a nice little clearance. And now my tool is all the way over here. The part is finished, or the roughing profile is finished. But I'm not through with the semantics of my canned cycle. I don't want to terminate down here because there's going to be a rapid move when the part finishes back to my original point. And I also have to consider that my G42, my nose radius compensation, is still active right now. I want to make sure that I cancel that. So my thing, I don't like to see 2-axis moves when it's retracting. Turning tool is not such a big deal, but when you see a 2-axis move on a boring bar that's coming out of the middle of your part, it can scare the snot out of you. So just for protocol, I always make sure that my final X move is going to put me back at the clearance plane where I started. So let's throw in the G40 to cancel my G42, and X, that guy right there, 2.85. That way I know that it's going to be a 1-axis move to return to my clearance plane rather than a 2-axis move. That looks like my entire shape profile, so now I can simply utilize the G code to express the end of the definition of the shape, which is G80. Now G81 started it, G80 completed it. There is the definition of my profile. My tool's still going to be sitting here at half mast. I need to ask myself, am I done with this tool? Yeah, I believe I am. So let's go ahead and send it home and put the machine in a condition where we could open the door if we needed to inspect the results of this cut. So we will go into rapid mode, and identical to our clearance move up here, we're going to say G0, X30, Z10, and then I'm going to put in M1, the conditional operator stop. I'm sure some of you already know this, but let's repeat it just in case. An M1, when the computer is running the program, it encounters M1, it'll look up at your key panel, and if this optional stop button is highlighted, if it's turned on, the little LED here is turned on, it treats that M1 as a stop sign, and it will stop until somebody comes up and either resets the program or hits cycle slam and allows you to continue on. If that light is off, as it is now, it'll blow through that M1 as if it were a yellow light in the state of California. They just blow through it. So that's our optional stop. It gives us an opportunity to inspect the part during prove out, but once we're in production, we can just barrel on through it. So I'm going to save the program and run it through the graphics again. This time I'm going to arrow over and utilize select and quit. It asks if I want to save it. Yes, I do. Now it not only saved the program, but it also reloaded it so that when I push the cycle slam button, the updated program is the one that's going to run. I'm still in machine lock, and my my feed rate and spindle are cranked up so that we can see this thing run. My program is showing, so by hitting the green button, it just starts running in graphics, not the actual machine. Now we're in our G85 cycle. I didn't tell it, make this pass, make this pass, make this pass. I simply defined the shape, and look at it go. It's doing exactly what I hoped it would do, which is rough out my profile, leaving 10,000ths in the X and 2,000ths in the Z for a finish pass at a later date. And then it went home and stopped. That pretty much looks like the rough shape of what we wanted to make, doesn't it? I think we're doing pretty well. So now let's go back to our process list and look at what we have next. We did our turn. We're ready to do a drilling cycle. We're going to pop the center out of this part. There's my ID print, and it looks like we're going to knock a 3/4 inch hole, 1.25 inches deep. Let's leave that up for a second so that we can then go over to our G-code list, and there's our face grooving cycle, which, yeah, okay, it can also be used as a drilling cycle, which is what we're going to do. Let's go ahead and pop up our G74 cycle document, and there's our list of what to do, plus the page in the book that expresses what's going to happen and what's required. Now there's a bunch of extra information in this that we're not going to use during this particular cycle, but we will cover it when we do the G73 version of this, which turns this entire process 90 degrees and does a grooving cycle. Let's go ahead and go back to our program by touching the Program Operations button. We're still active here, so edit, and we will cursor down to the end of our tool call, and we're ready to follow along with the process that we have right here. Move tool to clearance plane, put tool in cutting position. Well, I could retype all of this information because that's what this is, moving the tool to clearance and calling up the tool, or I can use some of the fancy OSP assistance like the copy and paste function. By positioning the cursor on the first line that I want to copy, I can touch F1 copy and it turns the cursor into a highlighted block. We'll move down here. I'm not going to pick up the G96 because, as you know, that's constant surface speed, and I want a constant spindle speed for this drill. A drill doesn't have a surface footage calculation since the X offset is 0. Now by touching the input key, that highlight block went away, but this information is on the clipboard in the Windows background. So now I'll just position the cursor where I want the information to be pasted and touch paste. Obviously I have to change a few things here, like this is no longer tool number 1, so it won't be N1, and my locations are incorrect, but I still have some basic structure. We're going to use tool number 7 for this. We're still going to maintain all of this modal information, but let's go ahead and fire the spindle to right where we want it to be spinning for this drill. 1750 is roughly 350 surface footage for a 3/4 inch drill, and so that's what we'll use. And we'll change this sequence number to match. And instead of being tool 1, offset 1, nose comp 1, this is tool 7, offset 7. And since we're not using any nose radius compensation, I don't need the first 2 digits. I can have them in there if I need that continuity, but it gives me a hint as to whether or not I'm using nose radius compensation if I omit it when I don't need it. And now this is no longer a CNMG rough. This is now a .747 insert drill. Now I said it was 747, it might be 750, doesn't matter. I'm going to use the boring bar to finish up that diameter anyway, so something close to that. And I turned on the coolant. In the previous tool I went to X 2.85, but in this case I want to go to X0 because that's where this tool is measured. It's gauged at the center line of rotation to the center of the drill, so put it at X0 and Z.1. Sometimes, because drills are a little scary and I don't want to bump this thing into the face of the part, I might go so far as to have it a little further out from the face of the part, but that's going to take a little bit more time to work in the cut. It's just going to save me a panic factor when I'm proving that my gauging is correct. Let's leave it there for now just to say I did. Now we're ready to follow along our list, move to part clearance plane, and call the cycle referring to the feature. So the cycle is, of course, G74. And I need to put in my parameters for how to use this particular cycle. Where is the X? Obviously that's at X0. And the Z is representative of the bottom of the hole. That's what it says right here, Z coordinate of target point. So that's where I want to finish this guy. And let's find my print, which we know is Z minus 1.25. So Z minus 1.25. Here's a little footnote for you. Even though we're at X, I repeated the X value in the can cycle. You have to do that. Otherwise, the machine generates an alarm and says, hey, I don't know if you are trying to shift off of the X center line and make this hole larger. This can cycle gives you the ability, like you see in this example right here, to make multiple pecks at different X values so that you could make a hole larger. You do that with a boring bar if you wanted to peck a bore. So by repeating where we are as to where we want to terminate, it knows we're not doing this little step over thing. So now I have my X and I have my Z. I need a depth of cut here, which is D, and let's give this a peck amount of, well, let's go 1/8 of an inch. Now, you notice on my example here, it's showing that this drill is pecking in by the D amount, and then it's doing this little short retract. That means that currently this is set to a short retract chip breaker style cycle. If I want the drill to come out of the hole, I need to add a value of L. See the L right there? It's specifying that, hey, I want you to make short retracts until you reach the L value. Then I want you to come all the way out of the hole, wrap it back in, and continue on with your D value until once again you reach L and do another full retract. So if I wanted to retract the drill after every peck, I could make the L and the D match. All right, that makes sense. But if my material is such that I don't need to get coolant down on that tip after every peck, I could, whoops, no 2 decimals, doggone it. I could make my full retract value a greater value than the D, so it'll do exactly what you see here. Short peck, short peck, short peck, full peck, short peck, short peck, short peck, full peck, and on until it reaches the target value of Z minus 1.25. Yeah, that's kind of neat. I use that quite a bit. Now we need a feed rate for the drilling cycle. In this case, we're going to go 3 thousandths per revolution. Keep in mind there are 2 inserts, so each insert's only going to be pushing half of that. But that's just a footnote. It doesn't really relate to our programming much. And now we've completed our pecking cycle, and I'm ready to get the drill, send the drill home. Now again, working on ID, as I mentioned in the previous segment, I don't like to make 2-axis moves when I'm working on the ID. It scares me. I never know if the X is going to wrap it into the side of the part, and this is a perfect example. I know full well that G74 is going to, after it reaches the Z target value, it's going to return to this position, but I don't always trust it. So by force of habit, I always put in a rapid move to get me the heck away from the part. And considering that those two are exactly the same, I may even go so far as to say, hey, get a little further away from the part, just so that during prove out, I am comfortable with what's going on. It's only going to add a couple of milliseconds to your cycle time, but it will save on your nerves, which, you know, at my age, I need that. I'm clear of the hole. I'm ready to repeat the go home and optional stop. So let's go G0. I don't have to repeat that because it's in G0 modal mode from the previous line, but hey, whatever. X30, Z10, and an M1. Let's go see what happens. Once again, I'm going to do my select and quit. Do I want to save? Yes, I do. And we'll get rid of all that information, go back to my automatic mode, turn on my program. Okay, so once again, I'm going to run this from the very beginning. Then on the next tool, I'll show you how to skip over some of this extra stuff. But this gives me a chance to flap my gums a little more as the machine is repeating what it was previously doing. There's our roughing can cycle. And you notice that even the graphics, because we have an increased feed rate, they're showing this as a rough finish. A rough surface finish. It's really neat. When we go and kick down to a shorter, smaller finish allowance, you're going to see that clean up. There's our drill doing short retracts until it reaches a depth of increments of ½ inch, and then it retracts and we're out of there. How cool is that? Now, one more thing I'm going to do to show you a feature of the graphics. I can turn off the solid and show just the lines of what's going on, or as I prefer, I just see the solid material. If that drill had taken off at an angle, I'd probably see an abnormality here, so I'm confident that I did it right. There's a few other graphics features that we're going to cover in a little bit, but for right now, that's cool. We did our drill, we did our rough, we're ready to move on to the next process. So somebody go ahead and ask, what is the next process, Charlie? Well, I'm glad you asked. Let's call up our, wow, I'm getting punchy, aren't I? Let's call up our process list. We did our turn, we did our drill, so we're on to the groove cycle. Excellent. Let's see if we've got a groove cycle here that we can call up. And there it is. Lost it there for a second. There's our OD-ID grooving cycle, and the page from the manual looks an awful lot like precisely what we did with the G74, but this time we're going to be pecking in the X-axis instead of the Z-axis. Clear enough? All right, let's get rid of some of this noise, and we will go back into our program, edit. Now, I have been utilizing this little scroll bar on the right side of the screen, which is easy to do on a PC, but on your machine tool, it's kind of difficult to touch this bar and with your finger and get it to scroll up and down. It's not difficult when the program is brand new, but as this program gets longer, that bar gets shorter, it's more difficult to catch. So let me show you a couple of interesting things. If you have the P300A control, you'll be able to scroll just like you would on your smartphone by touching the screen and swiping in the up direction. It will scroll down for you. But if you have an older control, there is a jump button here on our soft keys. When we use the jump, we have the ability to select last page, and it jumps to the end of the program. Right now, it doesn't hurt me to cursor down or one of the other means of navigating the control, but as the program gets longer, that jump becomes a lot handier, more, wow. Yeah, it becomes easier to use the jump button than it does some of the other features. Let's call up our groove tool. Anybody remember which what we did to copy the tool block? We're going to highlight, find our copy button, highlight all the way down. We're going to use the G96 for this cycle because the groove tool is going to be working on a different diameter. So we'll highlight the whole thing and push our enter button, skip down to the end, leave a line so that we can separate our drill from our groove, do a paste, and change our data here again. Now our groove tool is tool number 4. G97M3S1000, N number 4, T, back, 404. I'm going to omit the first 2 digits because I'm not using a nose comp for this. And this is a 0.0935 wide groove tool. M8, that's good. X 2.85, Z.1, that's just fine. And let's give it a little less on our surface footage just so that we know, hey, all right, we did something different for the groove. We're positioned right in front of the part. Show me the part. Right here. So I need to move my tool from this clearance plane to where I want to start the groove. And in my case, I choose to start at this back surface and work my way forward. So the first motion should be Z minus 0.380. That's this 200 thousandths wide plus the 180 of the lip. And so that's where my groove is going to start. I think I'd like to leave a little bit for a finish allowance. So instead of being 380, let's take it to 378. So there'll be 2 thousandths of cleanup available on this wall right here. So now I've moved into position there, but I'm still all the way up here above my raw stock. So let's make a rapid down to something that's closer to the 1.5, but obviously not touching. X, let's go to 1.6 because I just like that nice round number of 50 thousandths radial clearance. Now I'm ready to call up my G73 cycle. So show me G73. We've satisfied all of these guys and we're ready to do our G73. Very much like the the G74 cycle, we need to specify which cycle we're using, our X, but now this is going to be the target point. Previously, in the G74, we maintained the position the tool was in, but now we're doing the OD grooving, so we need to put our target point in there, which is 1.325. 1.325. However, I do want to leave a little bit on the finish, so let's take that to 335. Now we need a Z target point. Our current position is 378. I want to make individual pecs moving out in Z, so our target point is going to be minus 180. Z minus 0.180. Oh, let's give it 82 so we have the finish, the amount of finish that we had on the front. And we want to give it a K value, which if we look up here, we'll see that the K is the shift in the Z axis. That just means how far over do we want to step. See that K right there? How much do we want in between our Z axis pecs? We know that the tool is 0.93 wide, so we want it to be less than that. And just so that our tool lasts, we'll make it just a straight 50 thousandths. Now we look over here and we see the D. Let's use a D of 0.05. That means it's going to peck 50 thousandths on the diameter each time it moves in, and then it's going to retract. And I also have, I can't quite see it, but I have an E right here. See that E? That E represents a dwell at the bottom of the hole, at the bottom of the groove. If I were not running a finish pass, I'd probably want the tool to dwell there ever so slightly so that the material will be cleaned up around 360 degrees of the periphery. I'm going to do that just to say I did. That's a little light. Let's give it 2/100ths of a second. If you make that too much, you'll experience chatter at the bottom of your groove. You make it too little, and you won't quite have a completely cylindrical groove base. Now we want a feed rate. Let's give it, say, 3 thousandths. Now here is a concept that I did not talk about yet, and it may have lit off a red flag in your heads. When I was looking at my Z depth, I said that was Z.380 minus 380, and this was Z minus 180. But wait a second, this face is being utilized by the front of the groove tool, and this is the back of the groove tool. Oh geez, well that could cause a problem, but Okuma has a way of compensating for this. If I add a T value in my G73 cycle, it knows to use whatever tool offset is currently active for the first part of the cut, but by the time it gets to the end of the cut, it'll use whatever offset value I put in my T. Aha, that works. That's clever as all get out. Now we're going to go through and make sure that that's set up before we verify this part. So don't dwell on it. Just know that we now have two offsets for our groove tool. The front is T04 offset 4, and the back is T04 offset 24. That way we have control over the width of the groove as well as the diameter and the location. If we only use one offset, we still have location and diameter adjustment, but no width adjustment. So that will terminate my G83 cycle, just like the G73. Just like the G74, I like to give it a command to move to a clearance plane just so that I know it did. I am well aware that the G73 is supposed to deliver the tool back to this location before it terminates the cycle, but I like to be sure. So there we go, X 1.6. Now I roughed this groove out. I'm ready to finish that groove. And let's do it with the same tool since we're already in position. I've moved out to X 1.6. Let's take the front edge of the tool, T0404, and move further in Z than this minus 380 motion that we have right here, so that we can use our G76 corner round. Let's go to Z minus 0.4, which is a good 20 thousandths deeper than the than where the face will be laid in. And then we'll kick into feed mode, and let's feed down to the 1.5 diameter that is the groove. And since we're not actually cutting anything, we'll move at a pretty good clip there. And then we will put in our corner rounding function, G76, and our terminal point is Z minus 0.380, and L. What's the unnamed axis here? It's X, and our unnamed axis is moving in the minus direction, so the L will be minus 0.01. I think 10 thousandths is plenty to break that edge, don't you? And then we'll give it a nice slow feed rate so that my fillet comes out pretty. Now I can finish down that wall to the final diameter in X, which is X 1.325. And let's go ahead and leave that 2 thousandths right where it is. I don't need to get too crazy with it. And now I'm ready to trace my tool along this OD to finish up that guy. So it's going to be a Z move, and I want to terminate at minus 0.180, but I want to make sure that it's using my secondary offset before it gets there. Now I already know that there's 2 thousandths on this wall, and I don't want to go run the tool into that because it's just not gonna be happy. So let's back this off by, say, we'll make it 75 instead of minus 180. So that means I'll be 5,000. Oops, that's the wrong way, Charlie. Y'all almost caught me with a mistake. So now I've left 5 thousandths here, and I'm going to pop back out and do a little fillet action there. My next move, I want to make I'm just going to kind of pull the tool away from the wall here. So let's go to X 1.335, Z minus 0.190. So now I just made a little angular move to get away from the wall so that I can rapid G0 to X 1.6, get all the way out of the hole. Following me so far? We've got half of this groove finished. Let's do the other half now. We're going to go follow the same process and go Z minus let's go 160 because that's that 20 thousandths that we talked about. We know that our secondary offset is active right now, so I don't have to do anything fancy there. G1 to X 1.5. That's our air cut, so we'll go a little faster. Then we'll do our G76 radial move, terminating at Z minus 0.180 with our unnamed axis of a negative 0.002. And now let's go down the wall to our minor diameter, which is X 1.325. I'd like to make that little move again. Let's just retract straight out, do a little angle move. X 1.335 by Z minus 0.190. And let's speed it up because we don't really need to go slow right there. Wrap it out to our X of 1.6 to get out of the groove. And now I've roughed and finished the front groove. I am not going to terminate this tool right now because I would sure like to come up here and cut out this this extra material here. I'm going to finish that with the DNMG 55 degree tool, but why not? I've got a groove tool in play anyway. Why don't I just get rid of the bulk of the material right there so that the DNMG can work a little less hard. So I need to clear a little further than 1.6. Let's take this guy all the way out to above this diameter. Let's say 2.1. That will put us above this thread right about here. And so now I can wrap it all the way back to my Z minus 1.2. And in keeping with my 2000ths clearance, that's going to put the thing a little further forward. And I can just I don't need a can cycle here. I'm just going to pop that tool in there. Let's do a G1 to our X final diameter of 1.90. Let's go 1.4 so that we have our clearance, and give it an F on appropriate feed rate. Let's go 2.85 all the way out. Whoops, there I did that little mistake without the X again. At least I caught it this time. And now we can G0 to X30, Z10, and an M1 because we are completely done with that tool. Everybody agree? So let's get rid of our print. Let's do our select and quit. Go over to our operations. Now, as I promised, I don't want to sit here and make you guys watch this this roughing tool every time we do a verification. So I'm going to bring my program up here, and I'm going to do a restart by finding the restart key. We're still in machine lock, so it's not actually going to move. But if I touch my restart and I call up the sequence number where I want to start, in this case N7, is it the first N7 or the second N7? I want to read the modal value, so I'm going to use the first one. And here is a little note that even the guys that know about sequence restart may not understand. Do I want it to update the graphics as it's going? Well, yeah, that's the whole reason I'm doing this. So we'll put it in effect and say OK. As soon as I hit OK, it ran through the program quickly as if it were physically running, and then stopped right where I wanted to start my slow verification. Oh, I started at the insert drill. My mistake. No big deal. Let's watch it. In order to get the machine to not give me an alarm during restart, I have to use this button right here, sequence restart, right now. And what it will do is it will index the turret to put the previously used tool in cutting position and place the turrets where they would have been if I executed the program normally up to this point. Now I can hit cycle start, and here comes my drilling tool. Would have been nice if I had restarted at N4, but you get the point. There's my grooving cycle. And there's my finish. Zoop, zoop. Uh-oh. Looks like I crunched. I didn't pull far enough out from the material before I rapided, and my collision avoidance software alerted me to that. That's kind of neat. So I'm going to fix that. Let's reset everybody. We'll get back in here. If you don't have collision avoidance, you and I both know that 2.1 is greater than 2.0, and so you wouldn't have even noticed that there's an alarm. However, I like the collision avoidance telling me, hey, that's closer than I'm comfortable with. So let's take this out to 2.2 instead of 2.1. That'll give me a full 100 thousandths of clearance. Select and quit. Auto mode. Now I'm going to pop in and out of machine lock so that it resets my turret, and this time we'll do a restart. Restart. This time we'll use the appropriate N4, enter. OK. Now it rapided through the graphics, and I can push my restart button. Give me my program, doggone it. There it is. All set to go. Cycle start. Groove, 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 and a finish, and a finish. Ah, it's still angry. Why is it still angry? I think I just didn't move far enough out. I'm going to fix this. Little time warp there. I fixed it by moving the total value out to x 2.5. That was enough to give full clearance on the on that tool so that my collision avoidance didn't interfere. So let's take a look at the full cycle. Groove rough, groove rough, groove rough, groove finish, wrap it out. I could probably put in another feed move to make it go a little faster right there, but either which way, we now came in and took a very slight amount of material. So now we have to, oh, you know what I forgot to do? I forgot to show you the offset, the double offset on this thing. So I went back to my tool data page here, and if you have the same looking screen, you notice that there are two columns for offset 1 and one for offset 2. This is the location where the machine decides where to send data from the tool setter, where to store it for each individual tool. I added 4 and 24, and by just copying the information from offset number 4 into offset 24, I was able to avoid having to touch this tool twice. If my tool setter were gauged properly, I wouldn't have to worry about this. But on the Z, I just took the calibrated value from the front of the tool and added minus the width of the part off. So 0935 minus 1103 is 2038. So now I have two offsets for that tool. And that's how I managed to get my groove with an adjustable width. Wow, that was a fun one, wasn't it? I think we're ready to move on to the next. Does everybody remember what the next process is? I don't. So let's call up our process list and see. We did our turn, we did our drill, we did our groove, and now we're ready for the finish turn. Wow, that's great because we really needed an easy one to digest. Let's go back to our program. We'll edit. Let's go ahead and do our copy function and our jump function. Jump last page. Cursor up a few times. There's the end of our previous, so we can paste. We know that our finishing tool is number 2, so we'll change this to 2 and change that to 2. Because we're using nose radius compensation in the middle of this cycle, we need to put in our 6 digits. This is now a DNMG, and it is a finish. Turn M8, deliver to position, call up our spindle. We're good to go. Let's look at our sheet for the 2-axis process G87. Moved clearance, cutting position, spindle commands, we've done everything. Call cycle referring to profile. And there is our little format. This is incredibly easy. G87 is my finishing cycle, and now I simply need to specify what is the definition sequence. If you recall, it was NAT, and it was our first one, so NAT01. Now the book shows you that you can have a U and a W in here if you like to have a finish allowance in your G87, but why would you finish allowance a finish allowance? You can if you say want to make this a semi-finished tool, but in our case, hey, as soon as we do this, we're done. And I didn't have to redefine that entire profile because it's already written in NAT01. So once we're finished, we will G0 to X30 Z10, give us the M1, and let's run the program all the way through, shall we? There's our cycle slam. We're going to do our roughing tool. Give me my program, doggone it. There's our roughing pass. And previously I told you that to watch this surface finish on the graphic, it knows that we're in a high feed rate right now, so it's showing it kind of rough. When we do a finish, it's going to smooth that out, which is just really it's handy as all get out. Pop my drill with the intermediate retract. And it's also, if you notice, when this drill comes out, it's utilizing a different color for each of the tools that are cutting, which also makes it very handy if you have a gouge or something, a feature in your part, and you're not sure which tool is doing it. This color is a great indication of what's going on. Now there's our finishing tool. Notice that it smooths out the roughing contour because it's moving at a much slower feed rate. And zip across the front. I probably should have sped that up in my NAT01, but I'll do that on my time so that the next time we verify this, it doesn't take so much time. But now we're done. It delivers the part back to our clearance plane, and then it's going to send it home, and we're done. So now we have roughed, we have drilled, we've grooved, we've finished, and we're ready to move on to the next process. And that next process is threading. We're ready to do the threading cycle. Let's call it up. We know that this is a 2" by 12 threads per inch, and our major and minor diameter is listed right here. And we have the document for G71 where we're going to see what the machine is asking for, plus a whole bunch of little optional extras that we can throw in while we're making a thread. We'll describe those in just a second, but let's go back in and take a look at our program. We're going to go Program, Edit. We'll do our tool call, copy and paste again. Let's use that guy just to say we did. We'll copy him and bring him down to the bottom, paste him in. Now let's change our values to the appropriate tool, N3, and we're going to do, say, we'll do 1800 RPM on this guy. As I'm typing, I'll tell you that one of the biggest mistakes I see people doing while they're doing single point threading is they're just turning too darn slow. It is true that if you run too fast, the machine can't keep up with the A-cell, D-cell, the inertia, the momentum, all of the physics factors that are affecting the machine. But also, too slow is going to cause the material to gall, and it's going to give us a pretty nasty surface finish. So let's keep this at about 1800 RPM, and we'll know that we have the ability to pump it up if we need to, just so that we get that tool coasting smoothly through the material instead of ripping and tearing. And we'll call up our G71 cycle so that we can see we've done all of this information, and now we are ready to call our cycle. G71 is our cycle, and let's see the values that we need here. We need an X, a Z, an H, a D. Well, let's talk about each one of them. The first is the X, and that's our target point. That's not where we are now, that's where the minor diameter of the thread will wind up being. So in our case, our engineer was nice enough to already give us the minor diameter of the thread. There it is. So we will put in X 1.893 and a Z, which is the target value again. And so we're terminating into a thread relief here, so it really doesn't matter exactly where we stop, as long as we don't go so far as to smack into this wall right here. We don't want the tool to gouge for us. So let's make the Z minus 1.210. That should be enough to get all the way through a complete thread in the last, but not smack into this wall here. The next value that we need is a D. Let's go ahead and look at that cycle again. It doesn't matter what order we put them in as long as we get all of our values in here. The D is the depth of cut of the first thread expressed as a diameter. So let's put in D.01 and allow me to explain that that's the depth of the first pass. Depending on some of the cut conditions that we will specify at the end of this cycle, that depth of cut may decrease as it gets down to the bottom of the thread. Helps to eliminate chatter in a lot of cases and extends our tool life. But by saying a D of 0.01, it's never going to increase above that D value right there. The next value we'll want to put in is a U value. This is a finish allowance for the x-axis. We're going to, the G71 will rough and finish for us, so this U will be taken out during some finish passes. Not a problem for us. Next value is an H, and if you look at your list, the H is a thread height expressed as a diameter. So our thread height is major minus minor, and we would divide it by 2, but because our H is expressed as a diametrical value, we don't have to. Let's just go ahead and say that this is 100 thousandths thread height. Now, I am not going to, let's make that a little smaller so that I can tell you what it is that I'm doing here. This H is a negotiable value. It doesn't have to be exact. The machine is utilizing this H value to dictate where the first pass is going to occur. It takes this X target and adds the H, and that's where it's going to make the first pass. So if you make this number larger, that first pass is going to be lighter. You're still going to finish at X 1.893, which is going to establish the pitch diameter of your thread. That's the only factor that matters here, is our pitch diameter. It's not going to change that value. So if that first pass turns out to be too heavy, we'll make our H larger. If the first pass is too light, we can make the H smaller, and it will it'll dig a little deeper on the first pass. Now we need a feed rate, which is 1 divided by threads per inch, and in our case that's 0.0833. 1 divided by 12 is 0.0833. There's our thread pitch. And now we're going to throw in a couple of M codes to let the machine know the type of pattern we want to use. Now let's talk about these real quick. We know that a threading tool has a cutting edge on the front and the back of the tool. One is plus 30 degrees, one's minus 30 degrees. But if you're cutting equally on both of those faces, you can cause undue tool pressure and some chatter. This can cycle gives us the ability to say, you know what, don't cut with both faces. By moving in a tool pattern like what you see illustrated here, each subsequent pass will go forward in Z by the amount that you've pulled in divided by, Pythagorean theorem, the 30-degree angle. And so it will always be cutting with the front edge of the tool. We can also make it stagger. So the first pass will be using this cutting edge, then it will move to the front cutting edge, then the back cutting edge, front, back, all the way down, so that it provides equal tool wear. And then we can also specify whether we want that in-feed cutting pattern to be equal cutting depth all the way down, or if we want it to automatically reduce as it gets towards the bottom. So I happen to be a big fan of this cutting pattern in steel, so let's use it. Right there it tells us M33, M73. So if I come in here at the end of my line and say M33, M73, now I know that it'll make this cutting pattern as it goes down towards the bottom of the thread. I don't have to do anything else for my threading pattern, so let's just take the tool home, X30Z10, M1, and we'll take a look at what it looks like. Get rid of all this stuff. We'll do our select and quit. Yes. And that was N3. So let's do a restart at N3. Enter. Make sure our graphic is in effect, so it'll go fast through all of this stuff. And now we'll use our turn on our program, of course, and use our sequence restart and cycle start. Here comes our tool, and it's making our cut pass. Now obviously in the graphics I can't see it, excuse me, even when it's physically cutting in a machine, you can't really see it staggering left and right using both of the cutting edges, but you'll see it in the result over using a straight pattern. So now I have rough, drill, thread, and groove. I'm ready to move on to the next evolution. And the next evolution on our process list is to deburr the thread. Now, this is pretty self-explanatory, but let's beat a dead horse, shall we? When I run this threading tool through this material, even though I'm using that staggered pattern that you saw, it's going to be a little cobby at the crests. We're going to have some burrs on the OD of the thread, nothing a little Scotch-Brite wouldn't take off, but this is a dynamite machine, so why not deburr everything inside the machine? Plus, I also know that it's going to roll a burr right on this front edge and one in the back too. Plus, we haven't even finished that thread relief. So what I intend to do is to take my finish turning tool and eliminate this burr, skim across the OD of the part to get rid of those burrs on top of the thread, and then chase out this thread relief. So let's do that. Go into my program, edit, and since I am reutilizing one of the tools I've already used, why don't I just go to that evolution? There it is, DNMG finish, and we will copy that process and paste its preliminaries. I also like to clarify my sequence number if I'm using a tool more than once. In this case, N2 was already used up here. It's not going to generate an alarm by any means, but I'd like the clarity when I'm running to know that it's the first time to use the tool, it's the second time, so forth and so on. So I like to add the NA, and that way I know that, okay, this tool has been used before, this is the second time I'm calling it up, and everybody will be on the same page. All of my other information is going to remain the same, and there is no cycle really that will help me with doing this this little contour right here. We already know that the NAT01 does a profile that will finish this guy and this guy, but it won't touch this surface. So rather than repeat the NAT01, I'm just going to use this tool and trace this little feature right here so that there's not going to be any additional cutting here that could potentially cause chatter. Let's just do a point to point in order to keep my life simple. Let's find my OD print here and have it ready so that I can give my my point to point for my actual profile. So I'm up in front and I would like to wrap it to a position that is somewhere down around here. Let's not waste time feeding across the front. So I will say we're going to go to X of 1.995. That's still a decent clearance plane. Z minus 0.4. And that was in rapid, so I don't want to encroach on the part at this point. That's why I'm still a goodly little distance away from it. But now I can drop below this value here, and let's just call this X 1.775 so that I have enough to use the G76 to a straight line move and cut this, recut that little angle there. So we will now shift into G1 mode and specify that we're going to do the not a radius, we want the 75 chamfer. We're going to wind up at X 1.995 and an L value of the unnamed axis, Z minus 0.075, and give it a feed rate of like, say 0.002 or so. Now I did not utilize my my cutter compensation here, and I should have. And I also have forgotten to move in my Z to the 1/2 inch. So that was a little bit of a mistake. Let's go G1 Z minus 0.5 and G42, and we'll make that a pretty decent feed rate. Okay, so now we moved in and turned on our cutter compensation. Didn't forget it this time. Made our move out to the edge of the part, and now we will make a Z move to right about here. So let's go Z minus, let's call that 1.04-ish, because it should be the 1,250 minus the 110 and then the chamfer. So yeah, 1.04 should be pretty good. And we'll give it a little bit faster feed rate since all we're doing is deburring. Now let's move to our miner, the bottom of the groove, the X 1.904, not 094, 1.904. And because we want to cut this angle in the back, I also want to make the Z move to our 1.250 minus 110. So we'll make that Z minus 1.14 and use our decreased feed rate. And the final move, Z minus 1.25. And then we will, now we're up against this face, we can move straight out to our G40, cancel the nose radius compensation, go out to X, let's go to something well above where our material is. Now we can G0, let's go back out to our clearance plane so that we're not doing a 2-axis near the part. And then we'll G0 to X30 Z10, just like we always do, M1. See how we did. And minimize. There's our operation. And let's do a restart at our NA2. Okay, as it's zipping, I'm going to turn my program on. Now I'll do my sequence restart and do my cycle slam. There goes my finish tool, cutting just the burrs off of the part. There we go. So now we've just deburred our threads, but there's a pretty good chance that we could have rolled that burr, especially if our tool starts getting dull, rolled that burr back into the thread lead. So let's just run that threading tool one more time through the through the thread lead in order to make sure that that's clean. So we're kind of chasing our tail. We threaded, then we finished, and now we're going to thread again. But hey, no big deal. We want that thread lead to be good. So let's just take our entire process here and we'll copy it. And we'll bring it down below our deeper of the thread. And we'll paste it. Change that to NA3, NA3, and everything else could remain the same, but I will find out the hard way that this original thread path made about 9 passes. We don't need that anymore. We only need 1 or 2 to clear through. So let's change this D value to something large. And I think that might be too much, but let's see what happens if I were to restart at NA, what was that? That was 3, right? So NA 3. When I say it might be too large, but we'll find out. Mathematically, the depth of cut cannot be greater than the thread height minus the added to the minor. So if it does turn out to be too much, we're going to get an alarm. Oh, looked like it was just fine. In fact, I probably could have gone a little more because it gave us 7 passes instead of the original 9. But no big deal. I'm happy with it. It doesn't take that long, and now we have a nice threaded part that's deburred and finished, and we're ready to move on to the next operation. So let's take a look at our process list again. We've now deburred and rethread, so now we're ready to do the boring cycle. Now the bore is just going to be a rehash of our G85 cycle. So let's grab any tool call, copy that, and jump down to the bottom and repaste it. And now we can change our values to our boring bar, which we decided was tool number 8. And change it to 8. We'll use our nose radius comp on this, so 80808, M8. This time we don't need to go to a clearance plane that's above our material stock. We actually want to go below the material stock and position the tool at the inverse of the clearance plane of where our drill is. So previously we were going to 100 thousandths above our material stock, and we know we just popped a 747 hole in there. So let's go to an X of 0.7. Oh, if we did 750, let's go 650 for our clearance plane on the boring bar, and we'll let's pump this up. It's probably going to run up against our rev limiter because we're working on the inside of the part, but hey, whatever. We're happy. We're just following along with the manufacturer's specifications. And we will repeat our G85 cycle at this point. This time our NAT is going to be the second definition cycle. So there is our NAT02, and we already know about leaving a finish allowance in X, a finish allowance in Z, and a depth of cut. Let's go 75 thousandths, and a roughing feed rate, and we'll give it something a little less than the turning tool, since a boring bar is never going to be as rigid as this. This time NAT02, our shape definition, we're also going to do a G81 cycle just like we did before. But this time our G0 is going to be out and above our finished diameter. Again, we're rapiding out this time for our positioning move, so this is how the machine's going to decide that we're doing an ID, and it will leave our finish allowance on the minus side of the wall. So our first move should wrap it out above our final diameter. So let's go to X1 point, let's do something like 275. 275. And then we can do our G1, G41, since we're on the opposite side of the part this time, and Z0 at an F of, yeah, let's go 5 thousandths. We can move at a pretty good clip here. Now let's break the edge here as well. We might as well deburr that. So let's use our G76 edge breaking cycle, put in our final diameter and our L. Unnamed axis is Z, and that's going to move in the minus direction. And since it's not called out, let's just put in a little 10 thousandths edge break there just to say we did. Give it an appropriate feed rate. Now we'll just continue on with our profile. Z minus 0.120 is the depth of this bore. Now we do have a called out 50 thousandths by 45, so we can use our G75 chamfering cycle. Our final diameter is X.750, and our unnamed axis, the Z, is moving at 50 thousandths in the minus direction. And we forgot to increase the feed rate there, but then we'll shift it down for our 2-axis motion. That's good. And now we'll just go down to our final depth, which will be Z minus 1.250. And just as I did in the previous, the OD cycle, I want to deliver the tool back to the X.650. So cancel our nose radius compensation, X.650, just as I did before, and then reference G80 as being the end of the profile cycle. Since we're roughing and finishing with the same tool, I don't have to do anything like sending the tool home at this point. I can simply tell it, hey, G87, let's do our finish cycle, and it's the definition of NAT02. Now I will follow my safety protocol and get the tool further away from the part just so I see my motion, and then go home to X30Z10 and M1. Ready to take a shot at it? Select and quit. Yes. Let's get rid of our print here, and I will once again do a restart. This time we're going to N8. Okay, and while it's doing that, I'll call up my program, let it go through quickly. Then we will do the sequence restart and cycle start. There goes our boring bar, doing exactly what we wanted, and our finish pass. Now let's talk about a couple of the little hidden features in the graphics that are going to help us out. We couldn't see what the bottom of the bore looked like, so graphics is going to help us out in a couple of ways. I could turn on my section, which then cuts away the part, and now I can see what the bar looked like, or the bore looked like. I could also, if the section isn't making me happy, I could turn on this transparent right here. That's a little more difficult to see, but you can certainly tell. Now I'm going to run that one more time, this time with the section off, so that we can see the bore itself do its business. As long as I have the section view on, it'll run through with the part cut away. Now I can see exactly what the boring bar is doing. The chamfer, the edge break, and the finish bore size. It came out of the hole as it should, and now I've got my bore complete. So now I've completed my entire part, and I'm ready to cut the thing off. Let's turn our section back off, and we'll program the part off tool, and then we'll run the whole thing in graphics so that we can see the entire evolution of our effort all combined into one process. Let's do another double check of our process list. We've done turn, drill, groove, finish, turn, thread, deburr, rethread, bore, and now we're set to cut off, the final evolution of the part. Whew. We've covered a lot of stuff, haven't we? All right, so let's edit. This time I'm going to retype everything for the part off tool. Just, for no apparent reason other than I feel like doing a little refresher. We have the sequence number that matches our tool number, N12, G0 for the rapid, G95 for inches per revolution programming, G97 for constant RPM, and let's fire this up at S1000. Then we'll call up our tool, T1212, and I'm not using nose radius compensation, so I don't need the extra digits. Woo! Cut off blade and an M8 for coolant. Let's move to our X2.85 by Z.1. Even though that's not where we're going to use the tool, that's a nice clearance plane. And now I'm going to repeat the G50. Previously we were using 2750 as our maximum RPM, but in this case I don't want to go that fast. We're about to make the part pretty fragile. It's just going to be hanging on by a little bit, and I don't want the spindle ramping up all the way to 2750 as this thing starts to separate. So let's knock that down to, say, G50 of S1500. That'll be a lot easier to manage. And we'll give our G96, our constant spindle speed, to S400. That should be enough to keep our part off blade in good condition. So now let's look at our part and strategize what we're going to do here. I'd like to break this edge. We're going to part off to the finished allowance. We're going to assume that we're not going to try to rechuck this part and finish this face. Now we know that you have to have a really high quality part off tool to do this, because if you do part it off right at 2.5 inches, if that part off blade isn't making a clean surface on the backside, then we're going to have to face this off in a second operation anyway. But let's ignore that for now and just assume that we have a really high quality part off blade and we're following some good strategy. So we're gonna part this off as a finished part. So I would like to break that edge, and if I just plunge in with my part off tool, obviously that's going to be a nice sharp corner at best, and it'll be a big ragged burr at the worst. So I'd like to take my part off tool and cut a little bit of an edge break on that. However, if I do that in one shot, as the tool makes contact with the material while it's transitioning here, I'm going to go from zero tool pressure, zero tool contact here, and as I swing that radius or my chamfer, I'm going to go from 0% cutter engagement to 100% while I'm interpolating the radius. That's not good. So my strategy is to come out here, go beyond the 2.5 and plunge in to make a little relief back here. Then I can swing that fillet without having all kinds of excessive tool pressure. So what we'll do is make that relief, then we'll pop back out and we'll make that cut. Then I'm going to use my G73 pecking cycle to clear down until we get, let's say 250 thousandths. We'll leave a 1/4 inch of material that will maintain the connection between the finished part and our bar stock. Then we're going to shift into a slow G1 and just knock that thing off into our parts catcher. Wow, that's a lot, but we can do it. It's not that big a deal. So let's start by rapiding from our current clearance plane to where we want to make our relief. So let's go to Z minus 2.635. I am not using 2 offsets for this cutoff blade. You can. It's certainly, I mean, we already know how to do it. We saw it in the groove pattern, but I also want to demonstrate how you can do this by computing the math yourself instead of the double axis thing, or the double offset thing. So I went to 2.5 plus the 125 part off tool width, and then added another 10 thousandths just to swing that relief. So now I've gone to X2.635. I'll shift into feed mode, G1, and then I'll just plunge the part to say, let's go to, I'm going to go to 2.5 at a fast feed, and then I'll slow down and go to, say, X2.4 at something a lot slower. That way I'm getting through the air a little faster, and we probably should make that 10 thousandths above the part so that we don't get bit by a tool that's gauged a little bit off. So now I've plunged in and I want to wrap it back out of the part because now I've made my relief and I'm ready to swing my radius. So let's bring this to x 2.6 and we will move the front edge of the tool back a little bit in Z so that we can swing our radius. Let's go to Z minus 2.575 because that is again still gauging by the front of the tool. So we want to take where our position is and factor out the width of the groove tool. So 2.575 should be plenty for that. Shift back into feed mode, and now let's feed down to the major diameter of the part, x 2.5. You may want to add a little bit here, but I'm going to go with perfect world and imagine that 2.5 is not going to touch the part. If your part off blade is gauged perfectly, then hey, we won't make any kind of cut on the OD of the part. Now I can use my G76 and go to my final length of the part, Z minus 2.625. Better make that a minus. That would suck. Now our unnamed axis is the X, so we will do an L of minus, and let's put in a 20 thousandths fillet there and a nice modest feed rate of F2. Now we're sitting right about here, and as we discussed a minute ago, let's use our canned cycle G73 OD grooving and peck it down to about a 1/4 inch. So X target, not 2.5, 0.25. There we go. And our Z is going to maintain at Z minus 2.625. And we'll use a depth of, let's go a 1/4 inch depth of cut. And my L, this time I don't need to pull the tool all the way out. So I'm going to make the L value greater than the distance traveled. Let's just say, 2.5 is the diameter. Yeah, let's just say L of 2.5, so it'll short retract throughout the entire process. And we'll give it a feed rate 0.003. So after it swings this, it is going to make the peck down to 2.3, but then it's going to return back up to here. And I just looked up and noticed that I did something that I told you I couldn't do. I just tried to terminate with the G76 without another linear move. Can't do it. So let's go X 2.4 so that now it will it'll have a straight line move after the fillet. Good thing I saw that. So we know that after the G73 performs, it's going to wrap it all the way back out to the major of the part, and I don't want to wrap it back in on the off chance that this thing wiggles a little bit. So I'm going to do a G1 at a terminal of X point, let's go 275, something above where I was here, so I don't come crunching back into material. But I'll give it a faster feed rate because we're just positioning here. All I'm trying to avoid is a rapid causing this part to wiggle a little bit, pinch my part off tool in the cut, and cause some catastrophic issues. Now that I've wrapped it in, I'm ready to deploy my parts catcher. Now some of you may ask, well, why didn't you deploy your parts catcher in the beginning of the program? Or I'm sorry, not the beginning of the program, but the beginning of this part off tool, in case the part separates during this. Well, for one, I'm counting on it not separating, but for two, if I deployed the parts catcher somewhere up here, that means all of the chips that were generated in this process so far are now in my parts catcher. Yeah, and when the parts catcher retracts, it's going to dump all those chips into my bucket, and I really don't need that. So why not allow all these chips to fall down into the chip conveyor and then deploy my parts catcher? I'm ready to deploy it now. So let's look at our M code process and find where our parts catcher is. There it is. M77 for advance, M76 for retreat. So let's just get in here and put in M77. And I'm going to put a note in there. You don't have to, but I like to put that little note so that I am reminded of what M77 is, because I'm chronic for forgetting that stuff. Now that the parts catcher is deployed, I'm going to G1 and go over center line with the part off tool at a feed rate that is slower than normal, so I don't leave a big abnormality on the backside. Yeah, let's make that go down to 1. By the way, at this point, if I wanted to, which in this case, yeah, hey, I would sure like to do this, I can shift cut conditions. I've been using G96 constant surface speed up to this point, but now we're only cutting off a little bit, so I could shift and say, hey, now let's do G97 S800, which is a lot slower RPM than we would have been going. And so what I'm trying to achieve here is to reduce the speed, the revolutions that the part is rotating as it separates. I don't want this thing spinning at 2000 RPM as it drops into the catcher bucket, because then it can utilize that rotation to spin itself out of the bucket. And yeah, I don't want to do that. So now I have slowed down my RPM to 800. I'll make my final cut. That should drop the part in the bucket. I can then move myself out of the cut. Now I always do it in X back to my clearance, back to a clearance plane, just because I don't know if the part off blade will have completely separated this part. And if I try to make a retraction move that's 2-axis or in Z first, I can damage my part off blade. So I would just as soon retract straight out and then do my M76, which is catcher retract, which will dump the part into my my bucket, and then I can G0 to X30 Z10, and I don't need an M1 here because that is the end of my program. Let's get rid of some of these extra line spaces and have it terminate right here. All right, so let's do our select and quit. Yes, get rid of our print. And now let's verify this from the very beginning so that we can see the whole thing. Right now, we believe we're finished with the part. And so let's watch the entire process from the get-go. It may take a little bit of time, but heck, it's fun, right? Our roughing tool, using the NAT01 roughing cycle. We remember that. There's our drill using the G74, short retract combined with full retract. Now we've got our groove tool, doing a little step over, an edge break on our groove, throw in a relief, finishing tool that's taking out all the rough that was left over from the original NAT01. Now our part is at finished diameter and should have nice surface finish on the 2-axis moves as well as the single axis. Threading tool comes back in and does the thread to final diameter. Then we'll call up our DNMG again, and this time just deburr the thread lead and the thread relief. Now we'll come back in and rechase the thread so that our lead is intact and our mating part will fit properly. There's our boring bar, roughing, and now the boring bar finishing. And it will go all the way home. There's our relief cut. There's our edge break. Now we're going to go into the short retract pecking cycle. There's our G83 and this G73 down to 250. Now it pulled all the way back out. fast fed back in, parts catcher deployed, and it's separated the part. It's going to go pretty slow there. Retracted out of the groove, and there's our completed part. I'm going to use my angle change feature, and we'll turn this thing. There we go. And we will, I'd like to see, anytime I change the angle, it erases the entire graphic. So let's do a restart at N12 so that we can see that the part off blade really did go all the way through to the to completely separate the part. There's our sequence restart and our cycle slam. There's the relief. There's the edge break. There's our pecking cycle. Every quarter inch it's retracting ever so slightly, just enough to break a chip. And now it left quarter inch. We fed back in quickly, shifted into 800 RPM, and separated the part. Wrap it out. We're done. Alrighty then, the only thing left to do is to physically run the part in the machine. Now obviously I don't have a machine connected to this, but I'm going to use my collision avoidance software and show you a couple of the ways to manipulate the fancy programming that we put in there. The first of which that I want to mention is the clearance planes that we talked about. Remember how I always go to the major OD plus 100 thousandths or 50 on the radius and a Z of 0.1. So what I'm going to do here to show you how that works is I'm going to slow down. This is exactly what I would do on a real machine, and then turn on my single block so that I can one at a time hit cycle start, watch it spool up so things don't get out of control. There we're doing 1000 RPM. There's my tool call. It pulled up my first tool, and then it's going to bloop, turn on the coolant, and you notice now, zoop, I watched it slowly come down. I was probably standing there with my hand on the feed hold button, and just wanted to make sure that it really stopped above the OD and in front of the face of the part. Let's angle that a little bit so that you can see that, yeah, well, okay, all right, we're in front of the part, we're off to the side, we're good to go. Once I see that happen, now I know that the tool gauging is good, and the only other thing I'm going to worry about during this, because I've already proven the cycle works in graphics, is I need to watch and make sure this tool is not going to go so far back as to clip the jaws. So I will take my feed rate back up to what it's supposed to be. Now I can take off my single block and hit the cycle slam button. There's my facing move. I feel comfortable with that. And now, right about now, I'm standing there with my hand on the feed hold button to make sure that nothing contacts the jaws. Looks good. After that first pass is done, I'm confident, so I can just let this thing run. Now, for those of you that aren't familiar with the collision avoidance software, you'll notice that, hey, wait a second, the blank is reducing its size before my tool gets there. Yeah, the collision avoidance is doing that. It is looking 2 blocks ahead of what's physically running right now, just to make sure that the collision is detected before it actually starts the motion that would cause the crash. So I skipped over, I left my single block off, but I would do that with each tool, the single block approach, just to make sure that things are working the way they're supposed to. We're about to kick into our thread. This is our finish pass, and it's taking its own sweet time. I'm going to do the single block again so that we can talk a little bit when the boring bar comes up. But here's my threading cycle, and then we will have the thread deburr, and chase the thread. Now, I turned on single block just now so that you could see the characteristics. If you haven't experienced this in a threading cycle, single block is kind of neat because Every time you hit the cycle start button, it'll make another pass on the thread. So this way you can walk through it if you're not confident that you're not going to kiss the back wall or something. Okay, so now we're going to do our roughing tool. I'm going to go back to showing you what my feed rate override single block on, and the reason I wanted to do this with a boring bar is so that you could see each time you hit the cycle start button. Go faster, Charlie, go faster. It executes another branch of the turning can cycle. And then as soon as that's done, I'm going to, let's take off the single block. I'll see if I can catch it on the finish pass. So I wanted you to see, looks like we'll do one more. And now we're on our finish pass. There it is. There's the bottom. Now this is the condition I was talking about a couple of times about a boring bar doing a one-axis retract instead of two. We're at the bottom of our hole right now. If I hit cycle start, that single block moved it to the X650 diameter. Remember, we put that in there to match the approach diameter, and the reason is for this guy right here. When I push cycle start, it retracted straight out. Single Z motion. If that X, if the final X does not match the initial X, you'll see a two-axis motion, and in general, that's enough to scare you to death. Not my idea of fun. So there's our cutoff blade. We do our relief. We do the edge break. And let's crank this up because it does take a couple of seconds. You notice that our spindle RPM is just gradually raising. That's that G96 thing. And as soon as that's done, we pull it out, move back in at a quick feed rate. There's our parts catcher deploying. We're moving down across X center line fairly slowly. The part would have fallen into the bucket. The bucket would have dumped it out. Looks like we did it right.